quello, mando lo screen.
Ci siamo.
Okay. So, good afternoon. Sharply it's 2:30. I'm not used to speak while sitting, so I'll try to stand, despite not being exactly at my best. And thank you very much for coming. It's a pleasure to see this room crowded. And let me extend the thanks to all the speakers that we're going to be having today and whose agenda is over there. I'm begin by introducing myself. I'm Davide Bacciu. I'm a professor here at the Computer Science Department. I work with machine learning, most of all. And after me, you will be hearing a certain number of people with a diverse background and diverse, let's say, expertise, which you, of course, will have time to see and discuss. And I would like also to thank, aside from the speaker, Vincenzo Lomonaco, who started the overall idea and implemented it at speed of light, just to remember to stay on the same topic. And so thanks, Vincenzo, for setting this up. And it was clearly very well directed effort. So without further ado, let me begin by introducing a little bit of the background here. So in my presentation, I'm going to be speaking about why we are interested in space as machine learners. Okay, so we are working as a research group on a topic that we call pervasive AI. I'm going to be saying more about that, and we feel that this theme is particularly well matching with the challenges, the applications, and the potential of the space and the space economy. So if you're wondering what pervasive AI is the concatenation of pervasive computing and artificial intelligence, but it's far more than just a concatenation of buzzwords. It's the idea of needing to crossbreed to a research field which is more, let's say, traditional of systems, computing, communication systems, and one field that is more about intelligence, data processing, and implementation of, let's say, applications that require human-like reasoning at some type of level. Why we call it pervasive AI? Why do we need a pervasive artificial intelligence? Well, I mean, the picture is the picture of a world in which intelligence is not necessarily needed to be centralized. Okay? We are already in a world in which the availability of computing power and of communication connectivity allow us to distribute intelligence, and probably does not only allow us, also suggests that is a smart thing to do to distribute intelligence rather than centralize it in the cloud. So what this picture is meant to represent is the fact that intelligence under the form of neural network or any other form of intelligence must certainly meet devices at the edge. And of course, it can still reside on the cloud. And ideally, the desiderata would be that those two, say, words speak the same language, not only from an infrastructural perspective, but also from the perspective of the learning models that we deploy there. Okay, so ideally, there should be the same language between the edge and the cloud, or else said, we need models that can scale from the very constrained setups that you have in the edge to less constrained, say, setup that we have on the cloud with the scalability aspect that you require. And what does space fit into the perspective is a different kind of edge, a very different kind of edge. But nonetheless, it poses the same challenges that edge brings together, which is the let's say the need of being very careful about the consumption of the resources that we are given in terms of communication, in terms of computation, in terms of energy. And if you want to think about what is a prototypical application in a pervasive AI setting? Well, think about a world in which you're given access to a certain number of sensors. I call them system sensors because they don't really need to be physical sensors. Our system measure both the outer world as well as the state of the internal system, and those are virtual sensors, but nevertheless they are sensors about the system. And the characteristic of this sensor is that of producing information in time, which should be consumed in time, of course, with certain timeliness requirement, but also with the ability to process the history of the signals, because making sense of a system out of a single snapshot in time, it's really difficult, and sometimes it's a lost cause. Okay, so we would like to be able, through, for instance, cloud or edge AI, to make sense of these heterogeneous data streams that enter our system. And why do we want to do that? Well, because in the end, what we might be interested in building intelligent sensors, something that transforms these system sensors, noisy, fast-flowing, heterogeneous, into some abstract sensor that tells us the state of the person, the state of a system, the state of a crowd, or tells us if the system, the crowd, the person is behaving according to normality, or is entering some form of anomalous phase. So we're talking about putting a system into the right context by analyzing the data that surrounds it. The way we describe this is essentially we need AI that it allows us to predict and learn what we suggest continually, because it's very difficult to characterize an AI system once and for all based on a static picture of our environment. Possibly when you shoot that picture on Earth and then you expect that picture to generalize in space. You want the system that you deploy to be able to work continuously, and that is the least expected, but also be able to adapt, to shift, to learn, to adapt to domain changes, to adapt to anomalies that might happen, and be able to be so resistant to those. And doing that into the wild, and I cannot imagine anything wilder than the space and the deep sea. So I think this is one of the motivating reasons why, as a pervasive AI lab, we're looking into this specific area. So if you're wondering what the pervasive AI lab is it's a joint initiative between this department of Computer Science, and the Centro Nazionale delle Ricerche, the Italian National Research Center, in particular the Institute for Science and Technology there. It has been founded in 2019. Well, the culprits are myself and Patrizio Dazzi, who at the time was a researcher at ISTI. Now we moved to the computer science department. And it grew up, I'm an AI person, and Patrizio is a communication and distributed computing guy. So we decided to team up because we felt that there was much space in the crossbreed of these two areas. That's why we founded the lab, which counts on some 50 members. We have several European projects that we coordinate, national projects, let's say industrial projects. And the focus of this lab is looking at AI and pervasive computing from two different perspectives. The perspective of designing AI models that are, let's say, optimized to work in a specific deployment environment. So taking into consideration the constraints of the communication, of the computing, of the energy part. Okay, so it's essentially AI research where we get inspiration to do our methodological advances in AI from the constraints that we experience in these, let's say, practical deployments. From the other perspective, Patrizio looks, and people like Patrizio look at AI as a challenge to devise specific computing, communication, deployment, orchestration infrastructure for AI-enabled applications, because we know that AI poses enhanced requirements on the systems as well. So what would be our recipe for pervasive AI? And that's from the perspective of somebody that does AI. Okay, so if I have to design AI methodology that is adequate for pervasive applications, what would be the desiderata? From my perspective, as I anticipated, the ability to deal with time-dependent data, the ability to cut them for time series, and to have a dynamic memory, an efficient dynamic memory of the past in order to make proper predictions and proper analysis of what's going on into the system. But we have to do that efficiently. We cannot wait and perform in batch. We need to be efficient computationally, in memory, in energy. It has to be a methodology that allows embedding, because we want it to be at the edge. So it has to be hardware friendly, but at the same time, we also want it to scale to the cloud. And so if it scales to the cloud, we also want it to be communication efficient, because as soon as you have the cloud in place, you're also going to probably need to communicate with the edge. So we need to design system models that are both hardware friendly and communication friendly. It has to be simple to train continually, because we want this continual adaptation, and it's not always easy, especially if you have time series in mind. It should facilitate, in general, distributed training, because we're in a pervasive environment. And as we are typically dealing with real-world deployed stuff, we want it to be robust and reliable. So how are we tackling this thing? Well, through, let's say, specialized neural network designs. For instance, we look at neural networks as dynamical systems, because they are things that with a memory that process information that inputs to the system. And we want them to be effective, as I said, on fast streaming time series. And one of the way we do that is we use randomization as a source of efficiency. So we use architectures that are powerful, but at the same time constrained in their adaptivity. Okay? Constraining the adaptivity allows us to obtain very, let's say, hardware-friendly designs, compact the memory requirement, reduce the cost of training the model. But at the same time, what we would like to have is strict insurance from the perspective of what it can be computed, from the perspective of how much we can take into consideration the memory of the history of the input signal, and the stability of this system is seen as a dynamical system. So we work also at this particular trade-off between stability, having stable system, and having high memory systems. And also we would like, in principle, to be this design so hardware friendly to be, in principle, deployable in hardware through neuromorphic implementations. And that's part of the job that we do. Just to make an example, we have experiences with deploying this kind of system in devices with 8 kilobytes of memory, with a fixed alphabet of weights, with certain properties that can perform online learning on this kind of devices. That 8 kilobytes includes also the operating system and the rest of the firmware. Other aspects that are relevant to take into consideration are the ability to learn continually, because we want the system, and you're going to be hearing more about this methodology. We want the system to be able to learn incrementally, to acquire new skills, to adapt to changes in the environment, but without forgetting, or forgetting only when needed, because we don't want the system to chase the last modification in the system. We want stability in the end, while we gain adaptivity. And also we would like to, we explore also AutoML, which is how you make model selection automated. Because if your system drifts very much, machine learning theory tells you that your model cannot stay the same. You need to change the inductive bias of the model. You need an efficient way to do it on premise, on the edge. And that's what AutoML gives you. You want to be able to learn without backpropagation, because expecting to reverse time goes against the laws of physics, and also it's very dangerous assumption when you're training a model in situ on the edge. Okay, so you would like, in principle, to have access to this mechanism that allow you to learn without backpropagating in time. And you want also, speaking about robustness, your model to be aware of its uncertainty. Am I good at the job I am doing? This is a fundamental question that even a neural network should be able to answer in order to be deployed in these systems. And we do so by taking a very pragmatic approach, not only just a design approach. We designed we have made available several libraries for continual learning, for the development and deployment of pervasive AI applications. Some other are coming. at some point Valerio will come out with this one. I'm going very quickly, and this has been developed mainly between in the context of some European project that I've had the honor of being leading, and that have to do in a way or another with this concept of pervasive AI in multi-agent systems. Let me get to the end, otherwise I'll eat somebody else's time. So thank you very much. I think that we will have time for the discussion. This was mainly an introduction. If you have a very short question, I will be happy to answer to it. Otherwise. If there is a quick question, I'm available to answer it. Otherwise, I leave the stage to Vincenzo. We can discuss it later on. In the interest of time, I guess it's the best possible thing. Okay. So, Vincenzo, come here. So I'll do the chairing for Vincenzo, but then Vincenzo will handle the session for me. So Vincenzo is an assistant professor at the computer science department. Is our bearer of the torch of continual learning. So I leave the stage to Vincenzo to illustrate some of the technologies and methodologies that we're developing with those activities. Go on, Vincenzo.
Thank you so much, Davide, for the kind introduction. Hi, everyone. It's a pleasure to be here with all of you, a large number of people. And so the intent of this presentation was to give everyone kind of a basic starting point to understand what we are going to say next, right, in terms of technologies, enabling AI methodologies that we want to use in the context of space. So as you have seen in the schedule of the workshop, I will try to cover this part. Someone else will try to cover the space domain that some of you may not know, right? Because you see there are a lot of people here that know a lot about AI, a lot of people that know a lot about space, but there's very little people that know about the things together, right? So I will cover this basic introduction on the AI part. And so this is why I call my title here, Artificial Intelligence for Space Applications. And you quickly see that this is mostly about machine learning, not really AI. Just to start out, I wanted to start from this slide. So for people that are not really into AI, it is important to clarify a bit the nomenclature here. Okay. So a first question I would like to ask you is, how many of you are familiar with the term artificial intelligence and know what it is? If you can raise your hand, if you know. Almost everyone, I would assume. But then, can you locate, let's say, within a Venn diagram, all these different terms and keywords like machine learning, neural networks, deep learning, right? So this may be a bit challenging for some. And so what I want to suggest here is that AI is not equivalent to machine learning. Okay, so we have an entire course. I see some of my students here that is all about things that are not related to machine learning. I'll stay here in this outer loop in space. So we will talk about mostly machine learning today because, well, it is something that we do within the Pervasive AI lab mostly, and it's something that is mainstream right now. Okay, so if you want to use AI at the moment, what's still being, let's say, discovered, and it's interesting in terms of research and development, mostly to bring it in space. That is a conservative, let's say, I can say that, I guess, space and domain. Well, we can do a lot if we use neural networks and deep learning. That is this newest flavor of neural networks that after, I would say, 2000 came into place with a lot more compute capabilities, harder to support it, and mostly big data, right? So a lot of data, high volume and quantity and diversity that we can leverage to learn by examples. And this is the next relevant concept that I want to share with you today. What's changing with respect to the solution we are developing for space and for the other domains in computer science as machine learning enters this realm. And so what we are doing is something completely, and I would say revolutionary in this sense, right? So the technologies and methodologies may change, but this is kind of, let's say, a pivotal, let's say, change in how we tackle problems in our daily life, right? We want to solve them, trying to automatize them. That is the core of computer science, right? Information technology. So in the past, we started with this. So we have some input data, some data we want to work on that is somehow describing the problem, and then we have an expected output that we would like to have, like We have an unsorted list of items, and we want to design an algorithm that is able to sort them and give us an ordered list. And so what we do as computer science is to find out, let's say, design the program, the algorithm, like a recipe that would describe how computationally we can tackle this problem in an efficient and effective way. Well, with machine learning, this changes, right? So we are not interested anymore in designing ourselves a solution of a problem, but we expect to have a lot of examples of problems, definition, like a lot of random lists, or let's say unsorted lists, and then the same list ordered. And then we would like the computer itself to find out the solution, well, the algorithm that in general would work with any kind of unsorted list and provide a sorted list. That's amazing, right? Because in a sense, this is the most difficult and creative aspect of solving this problem. Now we would like to automatize this process, and this is why we call it artificial intelligence, right? So machine learning is amazing in terms of possibilities and unlocked well, potential, I would say. But it is important to know that something that may appear magic is also counterbalanced by a lot of problems. Okay, so we have an entire life cycle management related to machine learning methodologies and technologies that should be accounted for, especially if we want to use it for real world problems, for specific businesses, right? So for real, not just for research or some crazy ideas. And it goes, with an iterative loop, as the agile methodologies we know for designing software, maybe some of you know, so that we cannot assume, this is very, very important, that once we craft an AI solution, it's going to be, let's say, perfect forever, and would maintain the same performance forever. So it is something that is continually evolving. We need to maintain actively, and it can be scattered down in several steps, grossly, of course. The data acquisition step, where we need to collect those examples that are relevant for the problem we want to solve. The preparation of these data so that they can be actually processed by our machine learning algorithms. And then a set of steps where we need to design what are the best, let's say, machine learning methodologies to use. There is not one single take-all, let's say, solution for everything. And then set what are the relevant metrics, what we want the system to achieve in terms of metrics, right? Something that we can quantize the quality of the algorithms we are using, we are crafting. And then there is a set of steps that is relevant to the application, say, utilization of these AI models, as we call them, after deployment into real systems and in complex pipelines that may not be related to machine learning at all, right? So, for example, I want to deploy my system, my model into a specific application of my smartphone that there are a lot of different technologies at play there. And we need to somehow understand how our AI model can fit into all of this and optimize eventually this process. Then after these numerous number of difficult steps that are essentially what a data scientist, ML ops professional is actually doing all day, then we need to start again after we see and realize that something is not perfect, something can be improved. Something is changing in the world, in the space, the domain application we are considering, and we need to update the entire system, starting again from data acquisition step and collection on additional examples that will better cover the data distribution we are trying to target. Oh, and it is important, this is a study from Dimensional Research, to note that 80% of the entire budget spent by companies working on AI is actually spent on maintenance, not to create the actual solution. Okay, most I don't know, CEO, they just consider, okay, I want to spend this number of Ks to develop the AI solution that then I can use in my company. Of course, I will spend a bit of electric energy to make predictions and use this actual model, but they don't consider this additional 80% of the cost that is indeed spent in the maintenance of the solution. Okay, this is very important to understand, and this is why then we should, as a research team, also focus on solutions like continual learning I've been talking about, that is mostly trying to update the system itself with more autonomy and efficiency. Okay, so another important term that Davide already mentioned, and we should try to consider and summarize quickly, is the automated machine learning landscape. So there is a lot of research in this area, and essentially what we're trying to automatize here is the role of the data scientist, right? So we want to spend a lot of time in choosing the right algorithm, the right hyperparameters that will make the optimization or training process of those AI methodologies something difficult to do and very full of frictions, I would say. So this is the traditional ML workflow that I mentioned already: collect data, try out different methodologies, then see how they work, and start again if something is not at the level we expect. The AutoML methodology and realm is all about automatizing this process, and it is divided in mostly two, I would say, two main, let's say, problems and solutions attached. So the idea of finding the best hyperparameters, that are this set of parameters that would govern the optimization process itself in a training machine learning algorithm, and something that is equivalently, I would say, relevant is finding the actual algorithm to use. Even though we have a data scientist that is able to perform an hyperparameter selection and do this job for us. Of course, the best possible world would be to have those two problems solved together while we are actually learning our prediction model, our AI system, right? So the cache problem is essentially this formalization, I would say, of this particular, let's say, better and more general formulation of the AutoML problem. It is about selecting the actual algorithms, for example, a specific neural network or a combination of different methodologies. And at the same time, while we're training, performing this hyperparameter selection is very daunting, especially for neural networks. The second, I would say, important part that I think is relevant also for space, and this is why I'm trying to introduce it here, is continual learning. So this is something I've been working on in the last 10 years, my research activity. So it's what I'm more expert about. And I'm still convinced this is a very good part that's still not part of the fundamental, let's say, and mainstream research in continual learning, and especially in the context of the application of AI more generally. And it's all about this idea of learning over time when we don't have access to all the data at once. And it is based also on the idea of efficiently update our understanding of the world based on the new information available and what's changing around us in an efficient way based on what we have previously learned. Okay, so this is a very natural, I would say, way of learning if you look at biological learning systems, but it's not something we are doing as machine learning technologies nowadays. So what happens today, even if we simulate adaptation, is collect a bit more data, accumulate all this data in, let's say, these remote server locations, possibly also user data, then retrain the entire system from scratch with a huge expenditure in terms of compute power and CO2 emissions, etc., and money mostly, and then redeploy this system when it is updated based on this retraining. So this is completely, let's say, not reasonable in terms of sustainability, since we are starting from scratch every time. But it's something that we still do, given the fact that learning continuously is tough and is a nice research question to take note, due to the problem of catastrophic forgetting, what Davide mentioned. So if you just continually train on new data that you are witnessing over time with this backpropagation algorithm at the core of neural network training, then you completely erase what we have learned before. Okay, so if you don't add some additional magic sauces to the mix, then this approach doesn't work. So over time, the last 10 years, people have come up with different algorithms, strategies to try to solve this issue and work towards continually learning machines. It was also a dream for by Turing himself in the notion of development of robotics and AI. They can be divided in 4 different, I would say, categories, like this fuzzy categorization. So the first one is the regularization category, where what we're trying to do is just regularize learning on these new data distributions, new coming data, while preserving the weights and parameters inside of a neural network, non-parametric model, that are important to represent the previously encountered data distributions, the data of the past. For example, the objects in an object recognition task that I've seen in the past and I'm able to distinguish. The rearchal approach is quite, say, more, I would say, is simpler yet effective, and is based on the idea of rearching knowledge based on the assumption that I'm allowed to maintain in an external memory a set of samples that are deemed relevant for the past, to represent the past. So instead of just training on the new batch of data, new samples I'm looking at, then I try to mix those samples with data collected from the past, a few of them, of course, and this naturally improves the performance of a continual learner model. And this is a basic, very basic, naive approach based on replay, where essentially what if you can read these pseudocodes, summarize what I've just said. So I'm just trying to maintain an external memory. In this case, it's called think RAM, random memory, as a set of previously encountered example. And as I encounter new data in this M.B.I batch, then I try to dynamically change the, let's say, subgroups into this memory that would represent the previously encountered batches. And I try to sample randomly from the current data distribution, data that I have access to, some examples, and then I replace eventually, if the memory is full, previously encountered examples that I feed into the memory. And then I use this random memory to train, let's say, or better update our model directly on this joint memory. Well, the other two categories are about a variation of replay that is called generative replay, where the idea is quite visionary, I would say, where we try to learn an additional model to generate back examples from the past. So in a sense, we have a parametric approach to replay. And this is known to work very well for some specific problems, especially low dimensional, not so well with high dimensional patterns like in videos or in computer vision domains, where this is quite difficult to do. But in theory, it can be quite interesting, right? It's like ourselves when we dream about things and we expect that dreams would consolidate memory, as some neuroscience discoveries suggest. And finally, there is an architectural set of methods that is based on architectural modifications of a neural network or a model, where we add more weights or we freed some others. So there are some changes that would preserve information that we encode into these weights in the past, and at the same time allow for more space, right, to learn new things about the present, essentially. So all of these ideas, in a sense, have some basic inspiration from neuroscience. So we have evidence that suggests that, well, there is architectural change in our synapses into our brain. So neural generation is something quite active. Regularization can be seen as some hormonal or different chemicals interacting with the learning process itself to consolidate a memory. And the same goes for the replay activity, for example, the relationship between the hippocampus and the neocortex, or the role of repetition in terms of consolidation of memory due to spiking activities. Another element that I'd like to discuss with you is what Davide mentioned to be quite relevant for efficient application at the edge, and it's reservoir computing. This is the name that cover, I would say, a larger set of methods that are based on this well, dynamical system interpretation of learning and inference in AI. And it's based with the basic idea here is to leverage what we know about non-dynamical systems in terms of theory and signal propagation and consolidation of memory inside those systems in order to reduce the number of computation we need to train a system that is still able to effectively solve some complex machine learning tasks. So what we would need, right, if we use a basic neural network, a recurrent or a feed-forward neural network in general, is those different weights that are connecting the neurons that are trained based on an optimization process, right? So we want to minimize the number of errors that a particular neural network is actually performing in a particular training set. And we want this function to be minimized based on the change that we operate in those weights. In reservoir computing, what we do is to leverage the notion of randomness and other properties of dynamical systems in order to let the state of the entire system evolve it by itself without interfering with it in terms of changing those synapses. So this is very useful, as I mentioned, in terms of speed up in the training process, and especially for time series echo-state networks, the system you can see here with the equations you can see on the right, very simple. Those are known to be very effective in line with recurrent neural networks like LSTMs, long short-term memories, and other state-of-the-art fully trained systems, but improving in terms of efficiency order of magnitude. Okay, then as a research group here at University of Pisa, well, by the way, I have all the sources and research works that we have done and are relevant, I would say, for the things I'm discussing at the bottom, right? So I will share this presentation and the recordings itself inside the website that we have created for this workshop. But in this particular slide, I wanted to talk with you about a particular connection between continual learning and AutoML that we have just introduced. And we have done with Rudy Semola, that we'll talk next at the end of the workshop. And is already connecting these two important dots together. For the two notional properties you would like to have in pervasive AI systems are about efficiency and autonomy. Efficiency for continual learning and autonomy for AutoML. So in this particular paper, we target I'll say a sub-problem of the one that we already mentioned. So we want to perform hyperparameter tuning. So given a specific algorithm, we want to find out the hyperparameters that would work best based on a specific set of data, but we do it in a continual stream of data. So what we would like to do is, well, find out, given a set of examples, what are the relevant parameters that would help us learn faster and better, but then update the selection as soon as we encounter a new batch of data, and like to fine-tune this hyperparameter selection over time as we are fine-tuning also the real parameters of the model that would actually make these neural networks work for solving a specific problem. In this case, it's image classification on Core 50, a data set I collected when I was a PhD. And so those are the results. So you can see that you have three main choices, right? So you have this stream of data. You can select a specific set of hyperparameters that would perform reasonably well. So you don't spend any computation. You just select the hyperparameters based on your own intuition, and you get the actual results after the entire training process over multiple tasks. Then you have this HPO strategy. So this hyperparameter selection strategy you would naturally use, not in a continual learning case, but you have a fixed data set, you run this algorithm well consolidated in literature, and then you come up with this set of magic hyperparameters that will perform better on your sample. And then we have our adaptive HPO strategy that, let's say, continuously improve over time in this hyperparameter selection strategy. And as you can see, this is, let's say, a bar plot that is summarizing the amount of hours you need to train the system in this particular case with different continual learning strategies on the x-axis. And you can see that the adaptive HPO strategy is significantly better. So you see that it takes half the hours it would take of an HPO strategy to run. And I didn't show it here. In the paper, we report the accuracy, so the performance in terms of accuracy of the system, being able to discern these different objects in a computer vision task, is performing reasonably well in line with the HPO strategy. It's consuming much more in terms of compute. And of course, this goes much better than selecting manually the hyperparameters as a data scientist would do. Okay, so just to close my talk, I guess almost in time, I wanted to already share with you what I believe to be interesting applications in the context of space, based on the technology we've just seen and what we have discussed in terms of new AI methodologies that would improve efficiency and autonomy. So I think that there are a number of those, but I selected three, and I will talk about two. So the first one is land observation. The second one is mostly about fault diagnosis, isolation, recovery, anomaly detection, just simplified also even more as a machine learning problem, and smart satellite communications. So for those three, I have good insights that it is a good moment, let's say, to invest as AI scientist in those, and maybe we can discuss this in the open discussion at the end of the workshop. But what I can say for sure is that the Earth observation domain, well, application is something quite concrete, and I would say the mainstream application of AI technologies at the moment. Also, considering the fact that those AI solutions will be run and are running directly on the satellite. Okay, so maybe you have different technologies, AI-based, that are running in the ground stations or for, let's say, applications that are relevant to space, but are not actually used inside the specific satellites, CubeSats, nanosatellites, etc. So here instead, we are talking about technology that is already being tried in space. So AI solutions are already performing something in space, at least in the experimental phase. So this is mostly about feed-forward and what they call stateless neural networks, so convolutional neural network, feed-forward neural networks, where we don't take the notion of time. We don't maintain a state inside the neural network itself, and so we cannot process time or time-varying signals, for example. So we can just have an image, process it, have a prediction, and based on that prediction, we can decide what to do directly on the satellite, but that's it. So those solutions are made mostly efficient through specialized hardware and specific AI methodologies to make these systems smaller and faster. So this is already something that is taking place. However, these solutions do not allow for training, for adaptation directly on the satellite. So once we have a model, this is frozen, it is deployed at that, and it's also a big problem if we want to change this system because the bandwidth and other downlinks problems. Yeah, maybe someone else will talk about those, so, some properties of those systems. And kind of the same happens for anomaly detection. So an important informative point for people in the AI space, I guess, is that from 2006 to 2009, well, 43% of small satellites in orbit suffered mission failure. So it's a very complex and hostile environment. And in order to understand that something is not performing as planned, there are many solutions already in place, right? But most of them are based on basic time windowing and thresholding systems. So we just look at signals coming from telemetry data or other sensor we have inside the satellite, and we say, okay, if this signal is exceeding a particular threshold, we know by calibrating those systems on Earth is going over the roof here, then we say, there's something that is not performing very well. But you see, this system is very rigid because if something happens here is under the threshold, and it's really a different pattern here, right? So something that is changed. We cannot detect it with just thresholding or just taking a small window. We lost all the information about the pattern. This is all that we study in terms of recurrent neural networks and reservoir computing, what I mentioned before, to be very relevant for this specific use case. So state-of-the-art solutions do not have this notion of time. So we don't have STMs running in orbit at the moment. And again, they suffer this problem of impossibility to adapt, in a sense, based on the new normality conditions that may arise in space after something changes. So this is what I wanted to talk about. If you're interested about continual learning in particular, we have a course online on YouTube. This is a reference course on continual learning made by ContinualAI and UniPi. It's about 16 hours. It's a PhD course that we ran here a few years back. And we have an upcoming conference on lifelong learning, the third edition of this pioneer conference on continual learning that will take place in Pisa at the end of July, from the 29th of July to the 1st of August. So it's a 4 days conference, quite cheap, I would say also. So if you want to join, please visit the specific lifelong-ml.cc website with all the information. There is also another, as you can see me with the koala as at the end. But no, that's because the name of the conference would be Koala Scholars, or this joke. Okay, that's it. Thank you so much, and I'm here to answer your questions.
We have little time, but we have time for questions. Including where do you keep
Can I ask a very naive question?
Sure, no, there are no naive questions here. So.
Yeah, this one is, so what is the difference between continual learning and online learning, if there is any
No, that's a very interesting and recurring question that I get in all my talks. So this idea of learning over time, that is updating your understanding of the world as you see more of it, and more of the problem you want to solve is quite, well, I would say pervasive in AI, regardless of the methodology. Okay, so we have the same concept with symbolic AI, with knowledge bases evolving over time, the same happened in other small communities connected to AI, although with slightly different flavors. But the entire goal of building your understanding of the world continually and base your new insights on what you already know, it's something quite natural, right? And in AI, we have always tried to mimic a bit nature in this sense. So in particular, online learning at this flavor of learning one example at a time. There is also a particular, let's say, sub-community that is talking about online learning as just a way to learn over a static data set, just one example at a time. So online stochastic data descent is something that has been investigated a lot. And in a sense, we are able to process very few data, one example in extreme case, and learn from it. So this is the main question, right? But it's not really about learning from evolving or ever changing or different data distributions over time. That is something that is quite difficult to do. And we have postponed a lot in AI and in machine learning overall, working with IID data. So data that are coming from a steady distribution and are identically distributed. So I can see, in a sense, all of them or a sample of all of them. I have a clear picture of what I'm actually facing as a problem. So continual learning tries to, let's say, remove this constraint in AI, this assumption on your data, assuming that you have an evolving data distribution. And we have studied in continual learning specific, so continual learning that is more recent as a term, as a community inside the deep learning bubble. We have been trying to generalize a bit this concept. So one example, multiple examples, different tasks, a single task, but with dynamic data, high-dimensional data like computer vision, NLP, tabular data, multivariate time series. So we are trying to generalize it and improve our solutions as much as possible. And the online continual learning community is still quite active, and we are trying to connect more among these different communities.
If I may, the perspective that it's adding is also knowledge consolidation. In online learning, you're not incredibly focusing on how much you're consolidating your previous knowledge. You're very much interested in being reactive to what's happening now. But consolidation of learned knowledge is very important if you want a stable and a reliable system. So it's the usual stability plasticity dilemma that is tackled explicitly by continual learning, not by online learning.
Thank you.
So I think in the interest of time, we need to move to the next presentation, but there will be time for broader discussion afterwards. So thanks, Corrado. Ciao. So.
Okay, so we'll take over, Davide, right? Okay, so while Rudy, you can set up the presentation that Filippo and Giovanni prepared and shared with us on Google Slides, so you should have access to Telegram, to the link. Let me just introduce very quickly the next two speakers. Okay, so Filippo Giannetti is an associate professor at the University of Pisa in the Department of Information Engineering. And his main research interests lie in the field of wireless communication, with particular attention to digital modem design, digital signal processing algorithms, and radio resource allocation. I think it is worth mentioning also that Filippo in 1992 also spent a research period at the European Space Agency, Research and Technology Center, and there he was involved in various activities related to digital satellite communication. So together with Giovanni Scognamiglio, sorry for that, who will present a relevant application in the context of satellite communication, and is a data scientist at M.B.I. SRL, a telecom company working here in Pisa, correct? Thank you.
Okay. Thanks, Vincenzo. Good afternoon, everybody. I am here not as an expert in artificial intelligence, but instead as a communication engineer working in the field of space and satellite communications that we'll present here some needs, some scenarios that can benefit from the application of the artificial intelligence toolbox that Vincenzo presented in an exhaustive way. And I think many of them could be very useful for our applications. Communications and space missions are together since the birth of the space era. The first flying item outside the Earth atmosphere was nothing but a radio. Sputnik 1 was just a sphere containing a radio transmitter. So every time a satellite is sent in space or a probe is sent in space, it must carry an efficient communication system on board. And all the successes of space exploration have been made possible also by the use of efficient communication systems. A few words about the frequencies. We are dealing with radio communications. It is important to point out the frequency bands that are used in space communication because those have some implications in the functioning, the reliability of the systems that we are going to consider. Currently, space communication rely on S-band, but mainly X-band. There are odd names that have been chosen by engineers to name some portion of the radio frequency spectrum. And in particular, the X-band is the most used currently, and the frequencies are in megahertz, so you can say also 8.4 gigahertz. And unfortunately, the growth of space exploration brought to saturation of frequency bands. There are tens of spacecrafts flying in the solar system, and all of them are transmitting data, and the bands are not enough for allowing all of them to communicate simultaneously. And the more, if we are considering the future, near future, or not so near, considering human colonization of Mars or human exploration of Mars, for instance, which is a target for space activities within next decades. Those activities will be enabled by wideband video streaming links. If we have humans on Mars, we need to see them. We need to stay in touch with them, despite the delay. The delay is about from 5 minutes to 20 minutes, depending on the relative position of the planets. But we need to stay in touch with them. And we need a video streaming, which is estimated more than 30 megabits per second from Mars. Consider that the current orbiters on Mars, there are 7 of them currently active, are transmitting at bit rates that range from a couple of hundreds of bits per second up to a couple of megabits. So we have to increase at least 1 order of magnitude in terms of capacity. This is not possible to do within X-band, which is crowded. There is no room for further transmission, for wideband transmission. So we need to migrate to the newer, wider band named the Ka band, which is located around the 32 gigahertz, and it makes available 500 megahertz of band, which is enough for video streaming from Mars, for instance. Unfortunately, space is a rather harsh environment for communications due to some issues I'm going to present now. First of all, we have to consider the huge distances we are facing. Distances can range up to 6 billions of kilometers when the probes reach Pluto, which is the farthest body of the solar system, and beyond, because some probes are already beyond this orbit. And this entails long delays, tens of minutes up to Mars, but a few hours for Saturn and planets up to Pluto. Also, the missions must rely on a precise trajectory across space. And during space, the spacecraft must accomplish a set of measures, a set of maneuvers consisting in course correction, gravity assist, flybys, and others. But during the mission, something unexpected can happen. You may remember the famous Houston, we got a problem. So a reservoir blew up, and the oxygen was dispersed in the space. So some malfunctioning can occur, and some phenomena can request to modify the trajectory. So it is necessary to have a possibility of modifying the trajectory of the mission during the flight, but not with a real-time control from Earth because of the latency, which is too high for a real-time maneuver control. Nevertheless, during the maneuver, from a communication point of view, it is necessary that the main mission antenna, high-gain antenna, is kept pointed to Earth in order to continue transferring telemetry and mission data and to receive commands from ground. And this should be done even if the spacecraft is correcting its trajectory. Also, the spacecraft should keep solar cells pointed toward the sun, and so on. So all those maneuvers should have some constraints that that must be met necessarily. But another kind of problems arise from the weather. We have weather on Earth, but we have also weather in space. Weather in space is of two types. Let's consider the weather determined by the sun, mainly the solar wind, the flux of high energy radiation coming from the sun, which is highly variable due to the 11-year cycle of sunspots, but also it can have sudden blows due to solar flares and other phenomena on the solar surface that can change the weather in space. The weather in space is the portion of space between the sun and our planet, or the planets in the inner part of the solar system that are highly affected by those phenomena. Some are very slow in terms of dynamics, some are sudden. And the impact on communication satellite and space probe is dramatic. High radiation can damage devices, electronics on board, and can also modify data on board, and modify the status of the memories to change bits to flip a bit from 0 to 1 and vice versa. It is a dramatic impact. You can lose completely mission data. And also there are ionospheric effects that can be triggered by the solar activity, can disrupt the GPS services, and also low Earth orbit satellite can be influenced by the expansion of the thermosphere, which is triggered again by the solar activity, which rises the highest layers of the atmosphere and increase the atmospheric drag on satellites, modifying the orbits. So a lot of things, bad things can happen suddenly often on satellites, and due to the unpredictable weather determined by the sun. But also on planets, you can have some kind of weather, even if the atmosphere of Mars is thin, it is there. The atmosphere has some effect on the activities on ground, especially dust storms. Mars has a thin atmosphere, but there are some winds that can create large dust storms spanning over or up to a few thousand kilometers. And the interesting thing is that the local dust storm can occur at any time during the year at any location. So a rover or a vehicle on the surface of Mars can face bad weather, means dust storm, without not a warning So it must adapt its mission, its operations on the basis of what is going on. And again, a communication with Earth could take too much time. If Mars is the farthest distance, which is about 400 millions of kilometers, communication will require one way 20 minutes. So it is a too long time to tell the rover how to behave in case of a sudden sandstorm. And the worst is the Ka band. As I say, the Ka band is necessary in order to have videos for future missions. Okay, but the highest frequencies, the more vulnerable are to phenomenon in the atmosphere, even on Mars. And the attenuation of a dust storm is the worst effect concerning radio propagation. So radio signals are affected also by dust storms. If we resort, NASA suggests using margins, so to keep transmission level higher than the maximum attenuation you could encounter. But this is a waste of power. It's not a wise way of operating. And the best thing is to find an intelligent way to adapt communication depending on the weather conditions. So to have an awareness of situation on the surface of Mars and to adapt communication link on this situation. Then, summarizing, we have that spacecraft are often too far to be controlled. Latencies are too high. The telemetry, tracking, and command link are not adequate for controlling because of their latency. And immediate action implies that the spacecraft cannot wait for human commands, and they should operate autonomously on the place. So this is where artificial intelligence can provide a great help in the success of a space mission in the presence of unexpected events, especially. So it can help in guiding the spacecraft and provide the space situation awareness. It is a knowledge of space environment, including the weather, and how to behave in those cases. Then, concluding, the last challenge is encountered on our planet. Every communication with the spacecraft should cross our atmosphere. And our atmosphere is a harsh propagation medium, again, especially for high frequencies. Rain, for instance, is a great obstacle for radio waves that creates a high attenuation. This is the attenuation versus frequency. And the increasing frequency, we got a higher attenuation. Each line indicates a given rain intensity. For a given rain intensity, the effects are worse as the frequency increases. So we have two kinds of satellites. So communication satellites or space probes are sending their data toward the Earth station, and the Earth station is suffering rain fades, so it's experiencing a signal which is losing power. While Earth observation satellites are observing from top and are monitoring radiation emitted by atmosphere. In both cases, we can exploit the Earth station or the satellite to have an idea of the atmosphere. So in case of rain, we can also exploit some intelligence processing in order to extract information from rain fades about the status of the atmosphere about us. Then, again, collection processing of satellite data is another big opportunity for application of artificial intelligence in space systems. So it is possible to process and to classify the signals and to detect phenomenon in atmosphere by processing the received signals. Each signal has a signature, as a sort of fingerprint of the atmosphere on it. And by intelligent processing, it is possible to extract a lot of information from the signals. So what is happening now is that Giovanni Scognamiglio will present you as a case study an algorithm that makes an estimation of rain based on the analysis of a space to ground link in at the microwave frequencies. Okay, I leave the stage to Giovanni. Si può fare. Vuoi il puntatore questo?
Grazie. So thank you very much. So yeah, I was invited to showcase my master thesis that I did here at UniPi. My supervisor was Professor Micheli, and I did it in partnership with M.B.I. SRL, which I for now work as a data scientist. And so, yes, as Professor Giannetti says, rainfall produces rain fades at radio signal received at Earth. And M.B.I. happens to have a network of those satellite receivers. And they saw throughout the years that whenever it rains, you had an attenuation in the signal level. And they started developing physically based intelligent systems, so probabilistic ones such as Kalman filters, for detection and rainfall estimations. And the task of the thesis was to explore machine learning capabilities for this precise task and compare it with the in-house physically based intelligence systems. So it was very challenging. And yeah. So rainfall estimation. Rainfall estimation is a key valuable information nowadays, especially regarding climate change. So whether for studying climate change, whether for farming indicators, if you can have a system that can produce early warnings for floods, it can be beneficial both for farmers and for local administrators in cities. And you have two types of instruments. So traditional instruments as a point measurement, think about a vase, a rain gauge, or more advanced ones such as disgrammeters, which produces rainfall estimation based on the distribution of drops. Or you have wide area systems such as weather radar and satellite images. All of those taken individually do happens to have major limitations, either in terms of reliability, spatial, and temporal resolution. Think about owning 100,000 rain gauges means that you have to maintain 100,000 rain gauges, or in CAPEX and OPEX. So weather radar costs a lot of money and they are not generally available. So there is something called opportunistic rainfall measurement. And the fun thing is that you can actually measure rainfall from an infinite amount of things, such as windshield wipers from a car. Based on the resistance of the windshield wiper when it rains, you can deduce the amount of rains. Yet you need something more scalable and more easy to measure. So one of those is microwave-based rainfall measurements. Again, microwave-based means that whenever you have a receiver, a microwave receiver, such as terrestrials or satellite broadcast receivers. Terrestrial broadcast receivers are mainly for phone telecommunications. Satellite ones can be for any type of satellite communication. The advantage is that it's very low cost because it's opportunistic, because you already have a receiver there, and you have huge scaling potentials. So you make an algorithm for one, and you can pretty much generalize it to any number of it. The core concept is, of course, electromagnetic waves get absorbed. They are vulnerable to rainfall. So pretty much the rain passes in front of the sensors, and you get an attenuation in the signal. And an elevated signal attenuation corresponds to an elevated amount of rain. Regarding commercial terrestrial microwave links, it's not really regarding space, but it was still a major source of information for this thesis. So it's a very well-established subject of research. You even have an open source R package that lets you infer rainfall estimates from commercial microwave links signal attenuation. So how do they do it? Most often they use a power law relationship, so a physical relationship between the attenuation in the signal and the amount of rains. And you have numerous deep learning applications that show that you have very superior performance by using machine learning algorithms for these precise tasks. The main limitation with CMLs and why, so remember, CMLs, it's terrestrial ones. SMLs are the satellite ones. The main limitation of CMLs with respect to satellite receiver is that for CML, you usually have to pass by the phone operators because they are the one that owns these antennas and those receivers. This comes to the satellite microwave links. So it has been heavily studied also in the past, primarily using physical algorithms. So the interesting things that enabled us to deepen this research is that you have a new technology that allows you to have an interactive connection with the satellite. So you don't need an internet connection to get the data from the sensor, and you can get the data from the satellite, which means that if you possess a large number of sensors of satellite receiver, even without internet connection, you can infer how much the precipitation amount in real time. So those sensors produce a stream of data, and you can literally have almost true state rainfall estimation from a constant stream of data without internet connection. So yes, as I said, the same technologies, the same algorithms that are applied for CMLs are also used for satellite, for SMLs, for satellite connections. And the research, well, of course, well, the most common research entails dense neural networks and recurrent neural networks. I highlighted some of the research that was available at the time, and more or less, the main, I would say, where the research ended was that there was no end-to-end regression algorithm for satellite-based signal-to-noise attenuation for rainfall estimation. And so this made the process even more interesting. So this was a bit the setup. So you have, those are the receiver, which are interactive, which means that they send the signal back to the satellite. The satellite is connected to a central hub where all the terminals are connected. And the central hub has a data warehouse where people, citizen, or anyone who wants to inform can access it to retrieve the signal-to-noise ratio, or if an algorithm is running here that can do real-time streaming rainfall estimation, you can access potentially rainfall estimation in real time. So a bit about ML methodology. A small premise, I removed a lot of the boring part, which was experimental in my thesis. So a lot of what I did was, I would call it hypothesis testing, which means that you design a certain neural architecture or a certain set of models, and you study the assumptions behind it, and you hope that they match data. I mean, it's kind of, you design it in a way that they match the data, and then you compare it in terms of raw performance, in terms of robustness, and in terms of generalization. So it means that if I'm training in a supervised setting to convert signal-to-noise ratio attenuation from a receiver in Rome, because I have a receiver and a dysdrometer both located in Rome, I want that this association also works in Pisa, also in Salerno, and hopefully in other places. This is not really the case. So what we saw is that the further you go, of course, the less is generalized as well, because the learning algorithm, the neural architecture, let's say, focuses on signals that are inherent to the location. But then again, for achieving larger generalization, you need either smarter algorithm or to train on various locations. So what you will see is the end result in terms of data preprocessing, detection capabilities, and regression capabilities, along with a visualization. Just a little slide on the methodology used. So validation technique was temporal holdout. We first did, so for hyperparameter tuning, for shallow models, well, I could afford to do a complete grid search, so an exhaustive grid search. For neural model, it was more complicated. And so I leveraged this Bayesian optimization that comes with Keras Tuner, where you try to treat as much as possible as a hyperparameters, which means number of layers, number of units per layers, and also different modules. So you can either enable or disable a model using a Boolean hyperparameter. It's very fun. It works quite well. The problem is you can get too fancy because the more you add combination possibilities, the more your grid search takes time. So yes, it's combinatory, and this is why studying the hypothesis and targeting precise modules was much more effective than just make a huge grid search. So yeah, data reprocessing. As the professors, sorry, left. Oh, shit. Really? As the professor said, so the data in space is extremely challenging to work with. You have scintillation, you have missing values, and you have power-induced operations, power variation. We can skip this. This is just the effectiveness of preprocessing. And so this is the final data set that I used. At every time t, I used one dimension, it was the past temporal dimension, and one dimension was extracted statistics at various time windows. So you make monodimensional training set into a multidimensional training set, pretty much. Try to extract as many possible information from the data. Screening phase is not really important. The AND module which I ended up with was a multi-head neural network architecture, whatever. A dense neural network that was taking as input the tabular statistic extracted at time t, and a recurrent neural network for the temporal dimension. Of course, both heads matched the assumptions behind both types of data. So yeah, those are the classification accuracy. There you are. So you can see very high AUC, very high precision, very high accuracy. But then again, it's easy because the data set was 97.5 unbalanced, so it's not really informative. And somewhat a good precision and recall mix. But then again, your precision varies based on the true probability of rain in the population. And so this gives you that. You have a classifier. Here you have expected precision of the model. Here you have the true probability of rain in the population, breakdown by months. And you know that the more probable your true positive class is in the population, the better is your performance, keeping everything else constant. And so you see a fun fact that in July, your detector has a precision close to 4%, which goes to 80% in December. If I have just 1 minute left, then it's done.
That's fantastic. Thank you so
very
much.
much.
Thank you. That was quite informative and completed this entire presentation with quite a lot of hands-on part for application-wise session. So do we have some questions? Maybe
if I have just 30 seconds, I just want to show you one visualization which will help you. Yeah, here we are. So this is the end result. This is the truth. In green, you have the ground truth. So the rain, those are rain events. So for a given day, here you have the cumulative precipitation amount, and here you have the same amount that was predicted by the model. This is minute by minute, and this is the cumulative one. So you can see the delta at the end of the event. And this is pretty much how you measure the performance of a regressive neural network on signal attenuation for rainfall. So that's it.
Very nice. Thanks. So I guess for the sake of time, we can move ahead, and then if you can stay longer, we can chat maybe. Well, at the end of this first part of the work, as we thought would be very nice to have a little break after Alex's presentation that is coming up. So we will have a 5 minutes break around 4, okay, and 15 minutes. Okay, so Rudy, can you help me just to check out if Alex is hearing us, and maybe you can remove your screen sharing and see if from Microsoft Teams we can present this presentation.
So let me see. Oh yeah, now I understand. Okay.
Sotto il bottone interrompi la condivisione.
Perfect.
Alex, can you hear us?
Yes. Can you hear me?
Yes, we can.
Yes.
Okay, so I don't know if you can see me, Alex. Hi.
Hi.
All right. Maybe Rudy, if you can put it like full screen, so that I don't know if we need this. Well, I guess at some point, Alex, you can maybe try to present your slides if you can share your screen. Okay, now we see it. Fantastic. You can put it full screen. Okay, let me just introduce you, Alex. So
Yes.
Alex is a distinguished research fellow in artificial intelligence at the European Space Research and Technology Center. And one of Alex's primary objectives is to establish a comprehensive framework that empowers neural networks to learn autonomously from memories and adapt to their environment in real time, utilizing unprocessed data from the real world. And Alex envisions these technologies as foundation for the new generation of energy-efficient, autonomous AI systems that are both intelligent and robust enough for deployment in space missions. I think this is quite aligned with my own research objectives. So it is a pleasure to host your talk, Alex. And so feel free to start when you're ready.
Thank you. Thank you for the introduction and for the opportunity to present. I hope, please interrupt me at any point if you have any questions or comments or if anything is unclear. So I will try to give you a broad overview of continual learning research at ESA. So the caveat here is that ESA is not really a research organization. We have much stronger ties with industry and you know, making things fly, which is fair enough. But as a tiny part of ESA, the Advanced Concepts team, maybe I'll move on to the next slide. The Advanced Concepts team is basically has a mandate to monitor and perform research, which is again quite unusual at ESA. So perform research on advanced space concepts and technologies, preparing ESA for disruptive changes. So this includes various emerging technologies from neuromorphic computing to quantum. Maybe I'll give you a quick overview of our projects. This is just a tiny snapshot. You can visit our website for a full list of projects. So at any given point, we have specialists in fundamental physics, biomimetics, artificial intelligence, mission analysis, of course, and materials science in various proportions. So there are research fellows such as myself, young graduate trainees and interns. Sometimes we also have PhDs, visiting researchers. We have both actually at the same right now in the team. So a very diverse team, and the idea is that putting together experts from different fields in the same team would promote collaboration at a very, as you can see, a lot of these projects are multidisciplinary, and yes, a lot of really good research comes out of this. So in this context, so this if you want the QR code for the ACT's website, I'll leave it there for a second. So you can visit and look at all of our projects. So with that caveat, not everybody in the team is working on continual learning. In fact, I am the primary person who's working on continual learning, although other people are working on AI from different perspectives. So I will try to give you a brief overview of the projects that I'm working on in collaboration with other people, and also other efforts that are sort of targeting continual learning at ESA. But first, I'll go back to the original question, which was already raised a few times. Why continual learning in space? Well, some of these points were raised before in previous presentations already, but I will briefly iterate again. Space is uninviting for humans, so this is how I see it as a logical sort of progression. So space is uninviting for humans. If we want to leave this planet for whatever reason, even to go to the moon, we're going to rely on machines, rovers, robots, probes, satellites, landers, and so on. Even if we don't want to leave the planet, great distances prevent real-time control. So this will mandate some sort of autonomy. It is becoming already evident that autonomy will play a big part in exploration as probes venture further and further into solar system and beyond. There is also scarce trading data, so we cannot acquire necessarily the trading data that is required to train a model as we would do normally with large volumes of data, and we deploy the model. We know exactly in what environment it is deployed. So, in fact, all of these assumptions fly out the window. For example, an early example of a failure was with the Spirit that had a failure in one or even two of its wheels. This rover. And the engineers had to work out a creative solution to make it drive. They actually ended up driving it backwards for some of the mission time. So this sort of these failures can happen anywhere at any time, and the point is we cannot go and fix or even. We might not even know for a long time that something has happened. So it is important to be able to handle various circumstances. Also with the lander that recently, well, everybody's now landing on the moon, but the Japanese lander that tipped to one side, it almost got it, but right at the end it tipped. So it is still operational. The question is what do we do with this? It's operational. We don't want to end the mission. We want to get as much data as possible. So we need a machine that can adapt to these circumstances. And also a point that I will raise towards the end again is space is also harsh for machines. So we need hardware support for continual learning and adaptation that can handle continual learning. So what can we do to enable this future where we have machines that learn autonomously and continually online, on the fly? So as a small snapshot of what we're doing in the team, specifically in relation to continual learning, I will give you a brief overview of one main line of research that I'm pursuing in collaboration with other people on a new spiking neuron model, specifically designed for continual learning. And we're currently testing it in some scenarios such as drone control and optical flow estimation. Another project is in collaboration with a student from TU Delft for onboard AI, continual learning for onboard AI, which is focusing on bursts, so spike bursts, again with spiking networks. And this is using a mechanism for collaboration that I will again raise in a second. I'll also show you a snapshot of some research that is being conducted again by a PhD student at TU Delft, who is currently also affiliated with the ACT, who is working on memristors. This is another emerging technology. This is more on the hardware side. And also I will mention two sort of more tangentially related activities, an ARTES activity, which is a more comprehensive activity targeting, again, continual learning for SATCOM systems specifically, and another honorable mention for continual learning with neuromorphic processes. So briefly on the continual learning with spiking neural networks, I mentioned that I'm working on a neuron model that is specifically enabled, specifically targeting continual learning. So this is a model that is very flexible and can be interpreted in many ways. I like to think of it as a plug-and-play neuron model that you can use in any context without having to think too much about hyperparameters that you have to tune, what data is coming in, what sort of pre-processing you have to do. The neuron should just take whatever you give it and work. We call the model empath. So here I would like to sort of highlight a specific assumption that, or not assumption, but a point of differentiation that homeostasis or adaptation is viewed as an enabler for continual learning. So we're thinking of adaptation and learning as sort of orthogonal processes, because adaptation can happen independently of learning and vice versa. However, put together, they work very well together, but they're not necessarily the same thing. So homeostasis can enable continual learning and it sort of sets the ground for a learning model to be able to learn, because we all know with problems such as concept drift, for example, whereas the statistics start to diverge or other circumstances that the model has not encountered in the past, the learning can be impeded, really, if this is not taken into account. So this plug-and-play model that we're developing as a strong foundation in neuroscience, it's actually using a few homeostatic processes that are observed in neurons, in biological neurons, such as adaptive membrane potential and spiking threshold. It also has a single parameter per neuron, which is optionally learnable. So it can be learned, or it can be set via heuristics or other methods. It supports all sorts of learning rules. So backpropagation is also supported. Local rules have been STDP, and can also be interpreted as a continuous, so classical ANN neuron, or a spiking neuron. So it functions. It can function very happily as a either or. it prevents saturation and dead neurons and so on and so forth. It is also inherently sparse, which is actually a very interesting point for specifically for multitask scenarios where catastrophic forgetting becomes a problem, where sparsity of activation, not necessarily sparse weights, but sparse activation can actually be of big help. I will just show you the last point that it preserves, this model preserves activity through it in deep networks. This is just it's probably hard to see here, but these are 10 layers of spiking neurons. So the horizontal axis is time, just time steps, and the input is at the top. It propagates very nicely through across 500 steps. It is not a learning task. It is just demonstrating the ability of the neuron to preserve activity in deep networks. So this can pattern can be represented all the way up to, I don't know, 10, 20, 30 layers of spiking neurons, which is a struggle for other spiking models. So a brief overview of some applications that we're currently targeting. One application is drone control. This is in collaboration with a young graduate trainee at the ACT, Sebastian, who is working on GNC nets, which is guidance and control nets. This is a concept that was developed at the ACT and TU Delft, basically a very small feed-forward network that can perform real-time control of a drone. And this network can be trained on optimal trajectories to fly in a certain trajectory. So here, I hope this plays properly. At 4 seconds, we start applying a constant bias of 1.25 meters in the Z direction. So this is vertical after 4 seconds, all the way to the end of the simulation. And the original network sort of fails to handle this. You can see the red trajectory. The drone just stays remains stuck at the top above the gates where it's supposed to fly through the gates. It actually cannot handle the perturbation, whereas the drone controlled by the M.B.I network actually gradually returns to the original orbit. That you can learn more about the GNC nets at our website. I've put the QR code here too. Another application that we're working on is optical flow on the fly. So estimating optical flow from events. So in this particular case, we're using synthetic events, but we're also looking at real-world data. Optical flow is very important, again, for drones. This is the application. So this can be performed on the fly, on the drone, on board the drone. So here we were testing the learning rates of, or the error rates of 2 types of neurons, the leak, integrate, and fire in orange, and our M.B.I model in cyan, which actually managed to learn better and it was faster during inference and training. So this is work in progress. We need to verify that the drone can actually fly in both cases on real hardware. So this is pending, but exciting results nevertheless. I will also present some briefly some efforts, as I mentioned, targeting membristas. So this is research conducted by a PhD candidate at TU Delft, also affiliated with the ACT, Zakaria Raj. So what is a membrista? Maybe many of you know, but just in case, membrista is a fundamental circuit element. So it is basically a resistor with memory. So the resistance is programmable with electric pulses, and it maintains sort of a memory of the current flowing through the membrista. It is basically continuous. Within a certain range. So it is possible to implement actually neural networks in hardware using membristas. And there are some efforts, again, with the caveat that this is not my own research, but presenting it on behalf. So I would be more than happy to direct you in the right direction, point you in the right direction if you have further questions. But overall, there are some, there is actual hardware that is being tested at various research labs. But why is this interesting? The memristor is inherently radiation resistant to radiation. It has very low latency and consumes very little electricity. So it also supports matrix vector multiplication, so we can perform normal neural network operations with membristas, and is therefore a very suitable candidate for AI accelerators, analog ones, and particularly onboard learning scenarios. What scenarios are we targeting with membristas? The one scenario that is relevant for continual learning is geodesy nets, which is another type of network developed at the ACT, originally based on the NERF idea. And the idea is to learn the shape of an asteroid on the fly. So as we send a probe to the asteroid, we take various readings, and we try to infer the shape of the asteroid. You can learn about the geodesy nets on our website. Again, I'm not doing them justice here. It is a very interesting research. But the point is that membristas could potentially be applied together with other technologies like event-based cameras. We're also looking at applying event-based cameras to some of these some of these research lines. Another brief mention of a project that we just started in collaboration with TU Delft, burst-driven continual learning for onboard AI. This is an Arianna study, and I've left the QR code there for Arianna studies. They're a funding mechanism for researchers to conduct studies that can be funded by ESA, investigating a particular topic, particular question. And in this case, this is a short study on using bursts as a mechanism to enable long-term potentiation or depression in spiking networks. Again, for application to onboard AI. So learning on the fly on board. This is work in progress that just started. I'm mentioning it because it's relevant, but no real results yet, although we're making progress. One brief mention also of an artist activity. So this is a more comprehensive activity funded by ESA on board continual learning, specifically for SATCOM systems. The goals are to identify potential SATCOM applications that could benefit from continual learning. There are many, from interference detection to anomaly detection, beamforming, and so on. Really a lot of applications, potential applications. The point is that circumstances change all the time, especially with such a dynamic system, such dynamic systems such as telecom satellites. So we want to explore connections between offline and online learning, and how pre-trained models can be enhanced potentially by online and continual learning, and also identifying suitable architectures for onboard AI. And last but not least, as I mentioned, hardware is very important for continual learning, specifically to be supported by the hardware. So neuromorphic hardware is also something of great interest to ESA because of the many promises. Some of them justified, some not so much. But in terms of power consumption, latency, and other properties that make them very interesting for onboard applications. And some of the emerging neuromorphic hardware, neuromorphic processors are very interesting, but not many support learning, on-chip learning. One example is the brain chip Akida, which we're currently looking at. There are actually several projects involving this processor, and we're interested in what it has to offer in terms of continual learning. But it is at least claimed that it supports continual learning, but it remains to be seen. But this is one topic that is very relevant, let me say. So
Alex, we are quickly running out of time. If you can,
I'm finished.
Fantastic.
Thank you very much. Wasn't very technical, but I hope I caught your attention. And please get back to me with questions or comments. And if you want more information about any of these projects, I can definitely give you that.
No, Alex, that was perfect. Thank you so much. Unfortunately, I cannot show you the audience, but we are about 50 people here, so they enjoyed your talk, I'm sure. So I don't know if we have space for one question, Max. Then I would kindly ask Arianna, that I guess is connected, to wait for 10 minutes, because I think we need it. So if we can postpone the following interventions of 10 minutes, then that would be great for everyone, I guess. So do we have some questions for Alex? Sure.
The question is, we have today already some technologies about the new architecture that need to be implemented for this kind of stuff in space that still robust for the radiation and the environment of space. And is today technology, or we need to wait a little bit for understand which kind of dimension and devices we need. If we hear
Could you hear it, Alex, the question, or should I repeat it?
If you could repeat it, that would be great.
I think it was mostly about the maturity level of the technology and methodologies that you mentioned. So hardware and software, if it is ready, especially considering this radiation, hostile environment, and challenges you already mentioned in your talk. So how much, say,
Yes.
ahead we are in terms of TRL and the possibility of applying those ideas in the real world?
Great question. So the ACT as a team, almost by design, performs research which is basically at TRLs up to maybe 3. I'm not super familiar with it, but it's very low TRL. There have been, I think, a few exceptions where things have progressed quite quickly to the next level, but as a in terms of maturity level of most projects, we're looking at 10 to 20 years ahead in the future, probably for actual applications, with the possible exception of hardware, which is actually probably paradoxically a little bit more more I would say well received.
Okay, yeah.
Because it is more tangible, I would say, and reproducible. So a lot of the software is still models and software, and I would say lower tier. Yeah.
Thank you again, Alex. So we will take 10 minutes break. We will reassess at 4:30, I would say, and we start sharp in time. Okay. Thank you so much, Alex. Thank you.
Cheers.
Thank you.
So we are ready.
Almost.
Almost. Yeah. We're almost ready. Just 1 minute. Okay, Arianna is ready. Hello, Arianna. So.
Hello, everybody.
Hi, Arianna. They are taking their seats, so a
No
couple of
problem.
minutes and we start.
Sure.
Yeah.
Okay. Please take your seats. We are starting. Okay, so I see already Arianna connected with the presentation already in place. So it is my pleasure to introduce you to the next speaker, Arianna Tibuzzi. Is a principal at Obloo Ventures, a venture capital firm specializing in deep tech investments. With more than Arianna has more than 10 years of experience in tech transfer and startup funding, and has played a crucial role in bringing revolutionary ideas from universities to the market. She has been involved in raising over 200 million for startups, focusing on identifying promising spin-offs and projects from top Italian research institutions. And their expertise lies in nurturing those ventures to success. So thank you, Arianna, for joining us today. And please go ahead, the stage is yours.
Thank you, Vincenzo. Hello, everybody. While Vincenzo was talking, I took the advantage of showing this slide just for a quick introduction. But since you already said many interesting things about me, I would leave space to present Obloo, the company I work with. Obloo Ventures is a managing company of deep tech venture capital funds. So we are, let's say, what is called advisory company, advisory managers, and we are a special team of investors since all of us, the 8 of us, have a technical scientific background. When I say scientific, it's because almost 70% of us hold a PhD degree. In my case, I'm an electronic engineer with a PhD at the International ICT School in Trento, at the University of Trento. And we can count also with other colleagues with PhD in physics, nuclear engineering, or aerospace engineering. And so, as you see here, the composition of our team has more than 120 years as experience in multinational companies, but also 60 years cumulated, of course, of research and tech transfer activities. On the left, you see the active funds, venture capital funds we are managing. The first one is a VV3 TT, tech transfer. That was the first tech transfer fund in Italy, started in 2017, funded by CDP, by our sovereign, let's say, sovereign bank, governmental sovereign bank, and the European Investment Fund. Now it is in the so-called disinvestment phase. So we are not scouting any more, let's say, deal, but we are trying to grow the value of our portfolio. While Galaxia, let's say, started 1.5 years ago. It's the national tech transfer hub on aerospace, funded by CDP, again, venture capital. Obloo is also a partial, let's say, investor in the fund, and we are focused on aeronautics, space, downstream, upstream. We're going to see this a little bit more in depth later. What I wanted to highlight as an investors talking to also several researchers today in this workshop, is that deep tech is a very special investment topic, investment sector. So 81% of deep tech entrepreneurs, of deep tech founders, think that investors that they met along the way really lack scientific and engineering expertise to assess the potential of the technologies, of the project results they bring forward and present to the investors. That's why I really stress the importance of having a team that understands technologies and speaks the same language of the researchers, because the approach for deep tech venture building is let's say, is a combination of the advanced science results with engineering and with design too. So what we let's say, what we designed and experienced in the last 15 years of managing tech transfer funds is this Discover model that starts really from digging to scout the strongest and most promising business opportunities. And we do this really talking to researchers, going to university laboratories, trying to identify the real results that could have a value on the market. And we design together with the entrepreneurs a pre-seed round, let's say what we call a proof of concept round, in which we invest in the phase where they can de-risk this technology. In this case, is also very interesting to use design thinking approach. We use it at a very early stage as picture the customer journey, so that even at the very beginning, the research team has an idea of the stakeholders they will have to talk to, of the need they have to address. And then after design, we try to define with them the product, so to prototype the product and freeze the architecture of the system, and to go towards a new round that is normally the seed round, where we will have the money to close the product engineering phase and to prepare for market entry. Afterwards, okay, there are several funding rounds, but let's say the most important for our contribution are for sure the pre-seed and seed. So what's the status of the deep tech investment in Italy? Recently, a report on the 2023 performances came out. So I reported here just a few graphs, but to show you that even if Italy is always lagging behind in Europe with respect of the total investment dedicated to startups, we have to say that, as you see from this graph on the left, the red line is the Italian situation. We are the fastest growing ecosystem in Europe. So compared to 2013, what we got in 2023 is 7.4 times the investment. And this is very peculiar of the Italian situation. So meaning that we're really trying to leapfrog and achieve the other countries. And on the right, I wanted to highlight also the growth of the spin-off companies that are, let's say, representative of the deep tech investment sector. Look at the value especially the value of all Italian spin-off companies that in 2023, so last year, was around 2.1 billion. So there's really a great increase in this portfolio value of more than 400% in 5 years. And always in the same report, we find a very interesting, also unique feature of Italy around space. So these are the top 5 funded industry in 2023 by country. Okay, Italy is on top. And they are benchmarking what happened in 2023 with respect to the year before, 2022. As you see, the space sector, so investment, venture capital investment in the space sector increased with an incredibly amount, let's say, with an incredible ratio, and especially Italy is the only one where we see space as a top funded sectors. So here, actually, this percentage, I wanted to recalculate the increase with respect to 2022, reducing the amount of the investment, cutting the orbit operation. Maybe you know about the orbit, but they raised 100 million euro in 2023. So of course, this number resulted a bit not fake, but I mean, for sure, the increment with respect to 2022 is more than 300%. So a very unique situation for Italy, and that's why we wanted to focus on aerospace with Galaxia VC fund. This is also the situation globally and in Europe. On the right, we have the European VC market. And space venture capital is still small with respect to the entire venture capital in Europe, 1.5%. It's divided by upstream and downstream investment. So this is this was, let's say, the intro to Galaxia, to the fund we are now managing from CDP. So this is the National Tech Transfer Hub, whose mission is origination, let's say. So originating new startups, new technologies. Okay, we don't originate new technologies because we search for them at TRL 3 or 4, and we accompany them through all of these phases, from technical incubation to business creation, from a short and small investment to a bigger investment with the seed round. We start talking to universities, and we go ahead. So we focus, especially since we have this origination mission, we focus on POC, the proof of concept investment that normally goes, let's say, they have a financial need from 200K to 500K, depending also if we're talking about upstream or downstream applications, technologies. But let me highlight that the development phase of proof of concept is really the most critical, since 80% of the life cycle costs of final products are determined at the POC stage. So we really want to spend a lot of attention and support for teams, for young entrepreneurs in this proof of concept stage. Then Galaxia can follow on, of course, with the seed round of around 1 million to leave some Series A, let's say, opportunities for later stage when you are on the market. Our focus are all topics related to space, aerospace, aeronautics, so upstream, downstream. Here I wanted to highlight the data exploitation, since we're talking about artificial intelligence. For us, that's an enabling technology. So we always look also at enabling technologies that are those platform technologies that can have several applications, not only in the space domain, but that can surely bring a strong added value in the aerospace domain, meaning a tangible and growing business opportunities. So let me recall that the global aerospace artificial intelligence market is an incredibly fast-growing market. It's supposed to achieve almost 6 billion in 2028 at let's say at a rate of growth of almost more than 43%. This is really one of the highest growing rate we normally see. Also, when we do our due diligence, most of the market have 12%, 8%, 20%, but 43% is really high. So you understand why investors try to scout for deals based on application of artificial intelligence in the aerospace industry. And machine learning is the most important segment. You already presented interesting cases for aerospace. I just wanted to highlight that, as we said, the space environment is not very hospitable for humans. So a robot and spacecraft will play most of the tasks in space. They are already doing it, but it will be more and more developed. And so artificial intelligence and machine learning can really help automatize these robots and analyze and deal and lead the decision. It's very important to give the possibility on edge, so on board satellites, for example, to decide without having to communicate to the ground station on Earth. And what we have considered, especially in the last year, is the small spacecraft sector. So with small satellites, we mean the satellites below 600 kilos. So the ones that are always represented in constellations. So every time we talk about constellation, those are all small satellites. And it's true that there is an effort of loading increasingly complex, let's say, experiments on board small sats. So thanks to the higher performance and reliability of electronics, and also thanks to miniaturized components, it's really possible now to bring on board the small satellites higher power, for example, higher level of computing power. When I say miniaturized components, I mean all those elements that are enabling to bring AI processing on board, such as a special solar panel that can be very light, but still deployable in space and can multiply the watts produced, reducing even the weight, or cooling systems. Of course, cooling system, miniaturized, very efficient cooling system that are able to dissipate the high level of power used on board small sats. So here are just some example taken from a NASA report in the avionics. So, for example, they mention FPGA-based software-defined radios. So it's a new adaptive way of communicating, of satellite communication. And they really think that reprogrammability should be automatized and will become an onboard feature. So the fact that any CubeSat mission, for example, could be reprogrammable is very, very useful for several applications. And here I wanted to give you an idea of the Galaxia's portfolio, which is using AI. So here, without mentioning the name of the group or we have invested in or the name of the company, I reported some of the technologies and the startups we invested in because they brought something really new to the space sector. In this case, both upstream and downstream. So, for example, talking about upstream, we see AI used for space situational awareness and space tracking. So, being able to track object even down to 1 centimeter, and so to protect space asset from debris, for example. Then we invested in a company that proposes a rendezvous and docking systems for in-orbit servicing, and they will have to develop a machine vision system based on AI to be flexible enough to have a servicer that can work and can repair and can refuel any type of spacecraft. So this would be very challenging. We have also neural networks that are called frugal, meaning that they are able to reduce the energy consumption and to make the neural network model much more effective in image recognition for downstream application. Then we have a board that is plug and play that helps, let's say, the manufacturing of any type of satellite from CubeSat to the big spacecraft, helping the recognition of each component by the processor. So you can attach, let's say, any payload or web or camera or laser to the system, and the board will route automatically the element with the CPU. So this really reduces a lot the design and the manufacturing of the small sats. Then we have optimization of optical inter-satellite communication and downlink communication, as well as always talking about upstream. We invested in a lunar drone, so a drone that is able to automatically navigate and explore lunar pits, searching for resources, so resource mining, but also searching for lava tubes that could be the best places to establish a lunar base. This is still a proof of concept, but they have a guidance system that is really automatic and effective. AI is also used in all our downstream applications, such as monitoring of critical infrastructure, highways, bridges, dams, but also, for example, by a startup that can measure the metocean parameters of wind and waves for offshore wind farms. And actually, this is what I wanted to tell you. I hope it was a bit different from the previous presentations.
Thank you so much, Arianna. That was fantastic. No, it was indeed very useful to complete our, let's say, overview on AI and the technology that we are building and the applications in the context of space, as well as the market that is now being created by those technologies and the problems we actually have and we need to overcome in space. So we don't have a lot of time, unfortunately. We're running very late in the schedule, so I think I don't know, Arianna, if you can stay later on, for sure we will discuss something more
Sure.
about the business cases and opportunities. And I would definitely start as soon as possible with the presentation from Matteo Geminiani. So Matteo is a PhD student working in the Space Systems Laboratory, headed by Salvo Marcucci from the Department of Civic and Industrial Engineering, right? And he's a research enthusiast with a passion for space exploration, and his work is mostly focused on the design and simulation of innovative space missions. And specifically, he delved into the development of small satellites platforms and their associated low-thrust propulsion systems for Earth observation missions, technology validation, and scientific exploration. So thank you very much, Matteo, for being with us today. And I think your presentation already here. This one? Yes. And then we can present it. So if you can keep it within the 15 minutes,
yes,
that would be fantastic.
I will try my best.
Okay.
Okay, so thank you, everyone. I'm also here on behalf of my professor Marcucci, who couldn't come to this workshop, but sends also his regards to the organizers and to you, audience. So thank you, Vincenzo, for your introduction. My topic will be more focused on space rather than AI. And just a brief words on our laboratory. We are quite new laboratory, founded like 5 years ago. And our head is Professor Marcuccio. We are a bunch of PhD students, some research fellows, and also the master thesis that are staying with us during the master thesis. And until now, we have graduated 13 students in these years. And our work is focusedly, we design space missions. Our, let's say, flagship project is this mission that we are working on with the Italian Space Agency and the 3 departments of engineering, and also example M.B.I here. And it's an IOD mission. It means a technological demonstration mission on which we will have 5 experiments in the domains of propulsion, telecommunication, and thermal management. And it's a 16 units CubeSat that we are working on now. But also we do some other kind of research. We work using balloons to do various missions. And firstly, also because they are a very powerful tool for education for students, because they can be easily built and operated by students. And also because they simulate really good the environment that you will find into space. And now I want to speak with you about space a bit. In fact, and we'll start with the environment. This is a real footage from one of our balloons. Just so you see, we are more or less near to space in the region which is called near space, which is about 35 kilometers altitude in this image here. And this is the balloon that carries the payload up into the stratosphere. Then it bursts, and then we recover the payload with always lands into trees. Even if we try our best to avoid that, but so let's don't speak about deforestation, because trees are there. We eat them all the times. But it's a really nice way to simulate the space environment. So when speaking about the environment, this is really important also for AI applications, right? So the first thing of space is that there is a very high vacuum. There is a high vacuum in space, and this causes a lot of problems, mainly related to the outgassing of the materials, which release the gas they have inside that. And also it makes heat convection really difficult. You don't have air to cool down your system. And this also, it's a worse problem because you encounter very extreme temperatures in space. When you're coming out of eclipse, you are going from like minus 100 degrees to 180 degrees on your solar panels. And this causes very high thermal stresses that needs to be dealt with. And as also Professor Giannetti was saying before, we have, of course, microgravity also. And so the structures we design need to be thought in this way. And we have a very high radiation environment, which is mainly due to a lot of stuff there, charged particles, and also cosmic rays coming out from the galaxy. They can even change 1 bit from 0 to 1 inside your electronics. And so the electronics that we use on ground cannot just work in space. They need to be specially designed for that. And so this is also something to be taken into consideration when designing a space mission. Then we have the real nowadays problem of space debris that are indeed a problem. As we are polluting the ground, we are also polluting space as well. And with the constellations that are being deployed now, this problem is just getting worse and worse. Even if there are a lot of projects on that, but space debris are indeed increasing and needs to be avoided in space missions. And also we have, as we said before, communication delays. And this is of particular importance in deep space missions where you cannot just have real-time communication with your spacecraft. And so automatic decision, for example, is a really important topic in this field. So just a very overview on how a satellite is composed of. And I deliberately made this picture very complex because I wanted to make you understand that when you deal with a spacecraft, you have a bunch of disciplines that you need to be taken into consideration. Like you have orbit mechanics to calculate your position, you have a thermal control system to maintain your temperatures inside, and with the altitude control, you move your spacecraft around, so you point your solar panels to the sun or an antenna to the ground to download your data. And you have, of course, a structure of the satellite, and you have solar panels that provide power, but not only solar panels are there to power our spacecrafts. Then you need to communicate, otherwise you're just a piece of metal flying into space, and you need to control and handle your data. And you see that every time you change something into a spacecraft, this affects everything. So one of the messages that I really want to convey through this speech is that also for AI, for example, when we will be dealing with one of these disciplines, the approach that, in my opinion, is really important to be taken into consideration is a system approach in that, in the sense that if you change something somewhere, you always need to be looking at the full picture of the mission, even from the design, but also from the operation perspective. Also because there are a lot of different kinds of space missions. We have, of course, the exploration of the moon and Mars, but also we have the astronauts on the ISS, but also we have sent a lot of interplanetary probes into the deep space and rovers to Mars. Then we have communication satellites. And you see, these are very different and unique scenarios for space missions. We have a GPS navigation constellation, and also we have Earth observation satellite, which are so important to monitor the state of the weather and the climate for the planet nowadays. Then we have space telescope, because we don't look only at the ground, but also at the sky from the space. And we generate a very big amount of data that nowadays are really challenging to be handled just by the human. So this is another topic for you, artificial intelligence expert, to address, of course. And also now, private companies are sending very big constellations of satellite. In the past, it was more one very big satellite. Now is a whole bunch of small spacecraft, the tendency, no? And so this, and also space tourism is will be something to be taken into consideration in the next decades. So this was just to give you a very full picture of the kind of space missions that are out there and all the different kind of applications you can think of, okay? Also, because AI in space was in the past slowed down a bit by the computational limitation that were there, and also the reliability of those applications, and also because of the fact that the space has a very funny paradox inside them. You know, we tend to think about the space domain as the domain in which the technology is at its very far edge, no? But also space missions are so expensive and so risky that when you have something that works into space, you never want to change that. And so this slows down also a bit the process. It's a very conservative environment. And this is something that I discovered through the years. And due to this, and also to the very specificity of the missions, AI implementation into space was, in my opinion, slowed down a bit. But nowadays, algorithms are becoming much more efficient. We have much more computational power on that. And thanks to the constellations, the amount of missions that is increasing year by year, we will have a lot of much more data available to work on for you. And also because the mission complexity is becoming so high that it's impossible to handle the amount of information that we are producing just by analyzing that as humans. We need AI to undertake these problems. So this was just a bunch of, let's say, discussion points that I wanted to raise. So thank you for your attention.
Thank you. That was perfect in time and very useful for people like me that are not really experts in the space domain. So very interesting and useful for everyone. So we have a remote talk now that I would directly proceed with Jakub. So thank you again, and maybe we can continue the discussion with your insights later on. For now, I would go on for the sake of time with Jakub. Are you there? Can you hear us?
Hi, everyone.
Yes,
Yep.
Now we can hear you. So maybe you can start sharing your slides, Jakub, so that we can see if everything is fine. Okay, fantastic. We can see them. So Jakub is an associate professor at the Silesian University of Technology and is the head of artificial intelligence at KP Labs in Gliwice. And he has been instrumental in designing the onboard deep learning capabilities of Intuition One, and has contributed to other missions, including Copernicus hyperspectral imaging mission for the environment, THESAT-2, and operations on a satellite. And his research interests span on deep machine learning, hyperspectral images, signal processing, and addressing practical Earth observation challenges. So thank you so much, Jakub, for accepting my invitation, and please go ahead with your presentation.
Yeah, absolutely. Thank you. Thanks for this invitation. Super happy to be there. And today I will give you an overview of the company and also on the challenges that we tackle practically every day concerning AI in space. So we are not that small company at the moment. We are currently around 80-ish people. We have quite a number of projects related to space in terms of both hardware, software, and AI. And our vision is to build autonomous systems, in short, and we are trying to establish our name in space business, and you'll see that we are targeting different aspects of autonomous operations of satellites. And to actually do that, we are also trying to capture the entire processing chain of the satellite. We built upon a couple of pillars that are related to the technology that we built. I think it's a pretty unique scenario where we have, all the pillars in place. You'll see that we are focusing not only on managing the spacecraft, but also very important aspect is in-orbit data processing. We'll talk about that in a second, because in space we can capture quite a lot of data, which is very difficult and costly to transfer back to Earth. So we need to take some actions to make sure that we can extract some useful insights from the raw data that is being captured in there. And on top of that, it's not only just Earth observations for satellites. We may also be interested in, using the data that, for instance, comes from the sensors of the satellite to make sure that this operations of the satellite is, for instance, safe. And to actually build a satellite, there are a couple of areas that need to be considered. I started with AI, and this is a very important aspect in our company. But to actually make this happen, we need other areas as well. So we know that we need in-orbit data processing to, run the algorithms that are artificial intelligence powered in space. But also to make this happen, we need software, which is, sort of obvious. And also we need hardware. We built our hardware DPUs in-house. To do that, we need electronics and all the things that relate to the hardware solutions that could fly in space. Because you can imagine that this is a very constrained environment, and this is an extreme environment for running things in space. There are also some aspects concerning, for instance, thermal management and understanding if things can work in orbit. And finally, we need to somehow plan the mission to benefit from that in space once it is in orbit. I think it is also unique that we have the entire production line, so we have all things that are important to build the actual satellite in place as well. And I think it's worth mentioning that we, in our portfolio, we have something which is called a smart mission ecosystem, where we have all things coming hand by hand to make things happen in space. So we have software, we have hardware, we have AI, and we can benefit from the components all together to build something which is, on the one hand, it might be generic, but on the other hand, it may be targeting a specific use case for in-orbit operations. Finally, we are pretty experienced in different projects. We strongly cooperate with ESA, with European Space Agency, but also with NASA and other entities. And you might have heard of our biggest project, which is Intuition 1. This is a CubeSat, which was already launched and it's put in orbit. It was actually launched back in November last year, and it is, currently in there. And what is unique and I think interesting about Intuition 1 is that this satellite is equipped with hyperspectral camera, so we can observe that we have almost 200 of spectral bands capturing very detailed information about the materials on Earth. And on the other hand, we have the in-orbit data processing capabilities. So we can take an AI model, we can run in space, and then we can benefit from running things in space. There are a couple of benefits why we actually may want to run that kind of techniques in orbit rather than downlink the entire data to the ground for further processing. So we'll get back to this a bit later. But there are two main objectives or goals of Intuition 1. On the one hand, we want to prove the technology. So we need to show that this technology might be used in practical scenario in orbit, because once again, we know that the environment is pretty difficult. It is extreme, and there are a couple of things that need to be verified before running this in practical scenarios. And on the other hand, we wanted to target a specific use case for which we can indeed extract the insights from raw hyperspectral data. So for this mission, we focused on soil mapping or soil analysis in particular, but actually Intuition One is, we call it in-orbit laboratory, so we can update the model once the satellite is in orbit. So we can fine-tune the model or even change its target after launching into the space. We do have some images that were already captured by Intuition One. Here is a single example of RGB image, but this is hyperspectral. So we can see that we have a fairly nice spatial resolution as well. And based on that kind of information, which is huge in terms of spatial and also spectral information, we can benefit from some insights that might not be visible to the naked eye. But on the other hand, if you were to downlink that kind of huge data, it would be super costly and it would take a lot of time. So in extreme scenario, it might be just useless after some time because this particular image is no longer useful for the end user. For instance, if we were to detect, let's say, a methane leak on the ground, then this timely information is super important for practical usage. And we built our technology to be generic. As I mentioned, we have the algorithms or technology that might be used in various contexts. So we know that we might capture hyperspectral data, but it also might be multispectral, meaning that we have a lower number of wider bands. And if you look at the downstream tasks that we may target for the raw data, the raw image data captured in orbit, there are quite a lot of different possibilities. So we can classify the image, we can do some semantic segmentation, we can do regression, we can do anything which might be related to extracting some knowledge from raw data. But also it's not only image that might be captured on board the satellite. I also mentioned the signals that are commonly analyzed. Those are telemetry signals that help us understand if we have maybe some issues concerned with the satellite in orbit. And you might also think that building AI solutions for a hardware that is still not in orbit is difficult because we do not have any ground truth data, right? So before launching into the space, we cannot capture real data because the sensor is not in orbit. So there is a huge question how to build, for instance, supervised learners based on something that is not existing. And there are approaches to tackle this issue, and I will talk about that in a second. Very important is in-orbit data processing because, as we mentioned, we want to extract useful insights as fast as possible. So if we can analyze something in orbit and maybe downlink some useful information just from space, it would be much faster and hopefully less costly in practical scenarios. So at the end of the day, we would have this information much faster when compared to now linking the entire raw data and then analyzing it on the ground. But usually, if we do anything with data analysis in orbit, we do that for a good reason. We may want to observe Earth, and we may want to understand what are the phenomena on the Earth based on remotely sensed data. There is a huge advantage of that kind of data because it offers us a lot of scalability. So we can analyze huge areas based on the image data, which is non-invasive, and it will be much faster to analyze that kind of large areas compared with, for instance, on-the-ground measurements. There are a lot of different applications where hyperspectral or multispectral or maybe wider satellite image data might be useful. Those relate to, for instance, environmental monitoring or detecting some events on the ground which would require some fast actions. Or it may also relate to, as we mentioned, soil analysis. So this would be an information to the end user saying that we might want to, for instance, update our fertilization process because this soil should be somehow updated. So the number of applications is super huge. You know, there are new applications that are emerging practically every day, and you know, depending on the actual use case, we need to design the onboard AI processing chain to actually extract that kind of useful information for the user. Here's the example what might be done with satellite data. Here's the example from Sentinel-2. So this is an example of multispectral image captured for a given area on the ground. And if we have, for instance, a time series of images, so if you have a series of images captured for the very same area in time, we can, for instance, try to quantify the change of the area of the forest in this particular area. So based on this extracted information, we may see that, for instance, some areas are, you know, something wrong happened for the forest in some specific areas. So we may have some, for instance, illegal logging or anything which might be targeted specifically for this area. So this would be the fourth dimension that might be also used for in-orbit data. We might take a number of acquisitions in time for the very same area on the globe, which, you know, gives us this fourth dimension for analysis. As I mentioned, we may capture hyperspectral data. So the hyperspectral data is an image with a number of bands, the spectral bands, which are you know, very narrow, and they may be very useful in extracting some information about the materials on the ground. If we observe this area by the satellite, then as we mentioned, downloading the entire data would be costly and it would take a lot of time. So we may want to, for instance, focus on some areas of interest. And this area of interest would be smaller, but it still be, you know, large enough to provide scalability. But still, if we were to downlink this part of image, it would be maybe too costly. That's why we want to bring AI on board to sort of bring the brain just close to the eyes to analyze the raw data and send just the useful information for the user. One example is soil processing. So this is what we already mentioned. Instead of, for instance, gathering the soil samples on the ground, we could try to, you know, image this part of the globe and try to extract some soil parameters that might not be visible to the naked eye, because we do have some additional information for hyperspectral processing. And we were also trying to bring to the community the data set that might be useful for building that kind of solutions. So we captured the airborne data, the hyperspectral data, together with in situ measurements of soil parameters. We organized a challenge, which was called Hyperview, and we co-located this in-site measurements of the soil together with hyperspectral images. And the task was to, you know, extract the information about the soil based purely on images. This was actually done 2022, and last year we finished with that. But if you are interested, you might still access this data together with on-the-ground measurements of the soil parameters, and you could try to build your own solution for extracting some soil parameters from hyperspectral images. And this is the kind of solution that flies currently on board Intuition One. And as I mentioned at the very beginning, it's you know, difficult to build solutions that are supervised based on the data that is not existing. But there are some approaches to tackle this. And for instance, based on the airborne data captured by the airplane, we can try to simulate the images that we expect in orbit on board a specific satellite. Here's the example for Intuition One, but we can do that kind of simulation for any other satellite, assuming that we know the characteristics of the sensors. So you'll see that, you know, there are a lot of things to be considered while being in orbit. What is the, you know, latitude? What is the atmospheric conditions that are also affecting the way we see the image? And based on that kind of simulation, or we may say that we built a data level digital twin of a satellite. We could try to simulate the data to use it for building the model to, at least verify if that could work in practical scenario for the data that we will capture in the future. And it is another example on why we have difficulties in processing the in-orbit data. Here's another data modality, which is signal, and this is just telemetry of the satellite. So the telemetry is the signal captured by a specific component within the satellite, and based on that kind of data, we may want to understand that, for instance, something wrong started happening in orbit. So we can take some additional action to, for instance, save the satellite. And an interesting thing about that kind of data is that it may be changing in time. So we may have some concept drift in time, but on the other hand, we want to avoid forgetting what we already learned from the data. So this is a beautiful example that we might, if we have the in-orbit fine-tuning, at some point we may also face the problem of catastrophic forgetting, which is very common to continual learning. And this is a practical scenario where this might indeed happen for real data. So this data might be correlated with the sensor characteristics. It may change in time because of some, for instance, mission-specific data. So this is where we need to deploy something which would help us deal with catastrophic forgetting. But on the other hand, we want to ensure that we have something which is compact and fast because we are in orbit. So we cannot perform a full replay, for instance, because we want to ensure that this is still possible to run on a very constrained hardware environment. And obviously, as we already heard in the previous slides, some solutions might be very specific. On the one hand, we want to have the technology that could be used in different missions, but on the other hand, we need to remember that the hardware or the sensors might be specific, and we need to build solutions that allow us to fine-tune the algorithms that are generic in nature to some specific scenarios that are and will be happening in orbit. So we need to also ensure robustness of the solutions, and this is super important to, at the end of the day, have something which is useful in practice, and it will deliver some insights from the raw data in orbit. So I think that's it. Would be happy to take questions if we have time, but if not, I'm around.
Thank you so much, Jakub. That was super interesting. I think your company, the startup here, is really showing some interesting real-world applications, and your work is very nice towards this direction and converting what we have been doing in AI and making it real for the space domain. So we don't have a lot of time, and we are eating up almost all the open discussion session that I was planning, but we have one last talk from Rudy Semola. So Rudy is a dedicated PhD student at the University of Pisa and co-founder of ContinualIST, the University of Pisa spin-off. His research interests lie at the intersection of continual learning, AutoML, and deep learning, and he has contributed to various projects during his PhD, including developing an AI as a service toolkit for human-centered intelligence, one that Davide mentioned the start of this workshop, and on continual learning for predictive maintenance. So Rudy, please go ahead. You have a 15-minute slot, and then we will start with the open discussion. Possibly left.
Okay. So hello everyone. Today, in this presentation, I want to in an easy manner present the entrepreneur project ContinualIST, the innovation technology that is automatic continual learning, and the potential benefit and valuable consequence that this technology could bring in the space application. So the ContinualIST entrepreneur projects came from different interaction with different companies. Essentially, the problem is the following: building and maintaining accurate artificial intelligence predictor. In short, the issue are the following: these complex and expensive loops are time-consuming and is expensive in terms of human and hardware resource. If you think about the fact in some specific domain, like the space environment, these are more important. So, for this reason, we want to innovate this process thanks to the ContinualIST software developer kit. We want to remove a redundant step, and we want to automatize the other step in order to make possible this process directly in the production environment. In this case, for example, on board. And of course, making possible continually learning AI predictor. We want to minimize the human in the loop so data scientists, domain experts could work in activities that are more cost-effective for the agency and company. The key advantages are, of course, time-saving, human and hardware saving. Last but not least, performance improvement, because work directly on the environment that the AI predictor work. So this is possible thanks to the technology automated continual learning. In short, is a collection of different area of artificial intelligence that is continual learning, automated machine learning, learning from structured data, reservoir computing that bring benefit in terms of efficiency, autonomously, and working directly on the environment that is on board in the case of space. So I want to give you 2 examples in order to understand the technology and the potential benefit in the space sector. Here is an example of object recognition directly on the edge. In this case, is on smartphone. In this case, we are a continual learning algorithm that operates directly on smartphone to recognize objects. This is a typical approach that is used in state-of-the-art approach. But here, if you want to improve the performance capability of the model by recognizing existing classes, the continual learning algorithm have the capability to do this. For example, we have an adapter and recognize well white adapter, but less well black adapter. Simply because in the previous data, in the historical data, didn't see this. So by gathering image in real time, it is possible to learn and improving the recognition capability. Like it is visible here. So and of course can recognize much better these objects. Another important capability of this technology, in particular in this case continual learning, is the capability to train and learn how to recognize new objects. In this case, we have a new object that is the stapler that never seen before. So, even in this case, by gathering some image in real time directly on the smartphone, the continual learning model is capable to recognize these new objects. Yeah, And of course, the same object, but different color, for example, like is visible in this picture. So this is an example of continual object recognition directly on the edge, on the smartphone. It is an example in which could be used continual learning in such a way the artificial intelligence predictor are efficient, the adaptiveness of this artificial intelligence predictor are automatic, but also can work directly on the environment that operate, in this case, directly on the smartphone. This is another example that the team have worked, in particular to anomaly detection task, in which I've worked to experiment with the NASA Curiosity telemetry data to satellite predictive maintenance. Even in this case, we're working on edge condition, and it is interesting that the results bring as a performance improvement of 10% and a computational cost reduced by a factor of 10. Again, in short, this is an example in which it is possible to create efficient artificial intelligence predictor and keep this model performance even in edge context or in hostile environment like the space. So this technology, this a bunch of this artificial intelligence algorithm is validated on laboratory. And now we are ready also to take transfer these research results to more practical use cases. The validation was done according to different computational resources. In the two examples that we have seen before, it was in the edge case, but of course, we are working also on server computational resource. We have also an alpha prototype in which we have a documentation available, public available on site, and a notebook in which it's possible to play and see how it's working in practice with a toy example. So, as I said before, we are ready to take transfer this research result thanks to the ContinualIST Entrepreneur project, and by using automated continual learning technology in order to enable the next generation of the artificial intelligence system. We have seen that this kind of technology, and of course the algorithm that came from our scientific activity, it's very suitable and valuable in different domains like deep sea, transportation, industry, and industrial robotics. Here in this presentation, I want to present you, in particular in the space context, with three main applications: intelligent space software to efficient mission operation activity, spacecraft operation to automated diagnosis and prognosis of the satellite, and space safety in order to, to help to solve with the contribution the space junk problem and realize a clean space. So I want to give you a further example of a spacecraft operation application in which the ContinualIST solution, in this particular case, could be realized by two co-products in which the satellite operator can work with the ContinualIST dashboard, in which it has an high-quality digital twin of the satellite, and in other words, a good representation of the satellite in order to predict the satellite state in the future. And on the ground, on board, it is possible to use the ContinualIST software developer kit to enable the possibility to monitor the satellite state and enable adaptive predictive maintenance. This is possible thanks to the team that it's composed by me, Valerio De Caro, Vincenzo, Lomonaco, and Davide Bacciu, with a strong background in artificial intelligence. But we are not alone. I'm happy to share with you that ContinualIST have achieved over your journey the trust of different stakeholders. starting here from the University of Pisa to international entity, and of course with entity that have aligned an interest in our technology and eventually built potential and fruitful collaboration with us. So, as I said before, in this presentation, I presented the entrepreneur project ContinualIST, the technology, innovation, automated continual learning, and I'm here to invite you, the audience that attend in present and remotely, to collaborate for the space innovation. If you're interested in a bachelor thesis on continual learning, for example, for Earth observation, space operation, or satellite communication, please feel free to contact us to share your idea with us. Of course, for researcher, professor, PhD student that are interested to create a synergy collaboration, we have different pathways. And of course, last but not least, we are hiring. So we are ready to share this entrepreneur project with talent. So thank you for your time.
Thank you, Rudy, for the presentation. So we have 15 minutes eventually to discuss open problems, challenges, interesting questions on your side. Related to everything we had seen during the workshop, all right? So there are a few speakers still connected online, others are here and gave the presentation in person. So any questions related also to the previous talks we couldn't address before due to time constraints are well received at this time. So are there any questions? Yes, we have one back there. Yeah.
What do you think are the main challenges from perspective of AI engineers like
So what are the challenges from an AI engineer? So I will repeat the question for the remote audience. So a person here asked what are the main challenges from an AI engineer perspective related to Earth observation. So I think that Jakub in particular has a lot of experience in Earth observation. I don't know if you want to intervene here. I don't know if he's still connected or not.
Sure, I can take this question. So I think the biggest challenges are concerned with the data. As I mentioned during the talk, preparing the data or even understanding what might be extracted from the raw data is super important, especially given that the Earth is not labeled. So we cannot assume that we have a lot of labeled data, but at the same time, we know that the Earth is very heterogeneous. So we usually have some underrepresented, very local data, and the big challenge is to have something which might be generic enough to deploy it at scale. And there are some difficulties or challenges directly concerned with the characteristics of the data, because on the one hand, we have highly dimensional hyperspectral data, for instance, but on the other hand, again, we have a very small amount of ground truth information that might be used for building that kind of models. So we, people might want to exploit the information that is already present in the state of the art. For instance, in foundational models, we may want to build, for instance, feature extractors that are transferable across different applications. So I would say that the biggest changes are mostly concerned with the data, and once we have that kind of model that is operating, another challenge is to deploy it on the edge device, which is again constrained with respect to memory or compute that might be available in orbit. If we are saying about the in-orbit processing, so there are another branch of difficulties that relate to building something which is efficient and which is compact. So we cannot afford having, big, huge capacity models in orbit because they might be just too large for deployment on the edge device. Yeah, so I would say that this is mostly related to data and to building something which is efficient enough to be run in orbit on a very constrained and I would say extreme environment for execution.
Absolutely. We have a comment by Davide.
Yeah, just to connect on Jakub's point, I think that there is a lot of opportunity if you're an AI engineer, an AI researcher, especially if you're not working for Meta, Google, or stuff of the sort, in doing research in this particular field. Because, I mean, that's not an area where the fact that you have a lot of compute power plays a difference. There is much space for creativity and the ability to invent methodologies, I think, because the scale doesn't matter in this particular case. So it's also, for me, at least personally, as an AI researcher, is an interesting playground because you can really make a difference based on how good you are at inventing methodology rather than how good you are at reusing foundational models that are being pre-trained by somebody with a large amount of data, say. So I think it's a great opportunity.
Yeah, another comment that I can add is that I think Arianna can confirm it in their portfolio, the Galaxia fund Arianna presented before. There is another company, Focus AI, that is indeed focused on the, let's say, efficiency of deep neural networks used for Earth observation. Yes. And so this is totally aligned with the second set of challenges that Jakub was mentioning, right? So making those models smaller and more efficient to make predictions directly at the edge. So there is a lot of activity in this area and a lot of interesting challenges for AI engineers and data scientists, as Davide mentioned, are quite at the level of small teams as well. So this is very stimulating. Then since I'm talking, I think it is also worth mentioning a conference that Alex is instead helping organizing. It's called Space, and is targeting indeed the same audience we have today. So essentially at the intersection of AI and space, okay, experts. So in case you are interested, I will link this into the website. Yeah, I see Alex there, and I will link to the main website, okay, that they have created. And I think this is something that is happening near, right, Alex? I don't remember exactly the date, but it is imminent.
Yes, the deadline is the 19th of May for papers, and the conference itself is in September 17th to the 19th, I think.
Fantastic, and we will try to participate ourselves. So Rudy is preparing something, so
fantastic. Great.
we'll meet each other there with some other people. Yes, we have another question.
Excellent.
Since he was showing a video of smartphone learning at the moment, how hard would it be to let the model learn by itself this stuff? So without the interaction.
Without
the interaction of the human.
Without the interaction of the human.
The interaction.
The interaction of the human. Oh well. Yeah, of course this is a laboratory, no, we can say use cases, so it's difficult to say in practice, no, in reality. This is one of the main challenge that we want to overcome. And yeah, I mean, in the example of the smartphone, for example, the human interaction is easy. Essentially alert that there is a new object, and this object is the stapler in the case of the video example. And after this trigger, we can say it is possible to get any data and then learn from this short amount of data that collected in real time. From the satellite, there is other context, the consequence that, for example, the trigger could be made by sensor data or by a system that is in satellites. And therefore, in this manner, it is possible to reduce the human intervention because this trigger is not made by a human, but by an internal system.
You mean something like, for example, a context shift or drift detector, which says you have to.
This is the problem to trigger how to update or adapt the model. Yeah.
I think there is an interplay between methodologies there. I mean, if you want to make this work, it's not just continual learning. It's self-supervision, it's weak supervision, it's detection of drifts. It's a whole set of methodologies that you need to develop and integrate into single system, possibly in a robust way. So I think that's really also where the challenge lies. And everything needs to be properly integrated with an adequate underlying neural machinery as well. So I think there is a very much space for this sort of co-design of multiple requirements altogether to come up with new technologies. But I mean, it's not just a single ingredient. I think. Yeah. The single ingredient doesn't really solve the complexity of the problem.
Yeah, I think more often when you want to overcome this issue of let's say a specific, supervision, like explicit supervision in machine learning, you need to still think about some hypothesis of the operational scenario in which you are applying this technology, right? So, for example, the same exact technology that you have seen operating on the smartphone with the actual intervention of the human that to actually put in front and hit the record button, let's say, for capturing new images of that object and then adding a label describing what that is in natural language. Was indeed the application in the context of identifying recycling symbols. So we use the same exact algorithms to work with ERA. This is an energy company running in Italy and especially in Emilia-Romagna, and they have this app that is called the Refutologo, where you can use this app to actually recognize recycling symbol in say different plastic items and commercial products. To directly identify where you have to throw the item once you have depleted. So we use this technology to improve the ability to do the detection of those symbols, starting from natural images, and without imposing the user to actually record the new sessions and label it. So with sparse labeling, like feedback, so I'm doing good and not so good, we remove additional, let's say, frictions that we added in the version that we developed in the laboratory. But assuming that users are using that product in a particular way, there are some constraints in how the system is used, and the objectives are specifics, So limiting a bit the scope of the application, you can always find some tricks where you limit the direct supervision or specific and explicit interventions from humans. Any more questions or curiosities? Davide?
You keep asking. No, I have a comment-question for Alexander. Can you hear me, Alexander? Can I come forward?
Yes.
Slowly.
Yeah.
No, I particularly like the picture that you presented in terms of works that deal with the continual learning, but as well with neuromorphic aspects and with memristors. So my view over that, my take over that is that we shouldn't be looking at those problems independently, but I mean, I think the crux of the problem is how you can get a neuromorphic learning model that can learn continuously, possibly with the adequate learning model all together in a single platform. Because I think it's easy nowadays to try and imagine how to get the things separately, but getting them packaged together as a single solution, it's not that straightforward. At least that's my feeling. I don't know whether this is also your experience as you're directly working with those technologies. It would be interesting for me to know your view.
Yes, yeah, good observation. Specifically for memristors, they're not very common, I would say. This is not something that you can just buy off the shelf, but also neuromorphic processors in general. There is, as far as I know, only a couple of commercial systems, so it's hard to assess, indeed. But in my experience, from what I've learned from interacting with these systems, it's actually that there's a big reality gap between what they promise and what is actually implementable. And everybody comes forward with their own problems and their own use cases, and these things take time to iterate and improve the hardware. Intel is now working on, well, they have been working for a while on Luhi 2. There's probably Luhi 3 coming at some point. BrainChip has the Akida platform, which promises that actually some continual learning capability with one specific scenario, so classification. It's something similar to what Rudy demonstrated with the phone, but learning on chip. But again, this is very restricted. If you look at the SDK and the implementation, it's limited to learning only the weights of the top layer of your model and so on and so forth. Yeah, I think, I don't know if I'm answering your question very well, but I think that there's still a lot to be desired from these platforms. There's definitely no single platform, as far as I'm aware, that can really implement anything anything that we want. Of course, you can write software that runs on a GPU, and the software is going to do everything you want. But the point is to implement it really in hardware. So yeah, I haven't seen anything like that yet.
If you want to talk about BrainChip, we're discussing with them through some contacts that we've held with the CTO of BrainChip, and I mean, we know what was the situation with that chip. At some point, we can have a discussion about that.
Yeah, I would be very happy to. Yes.
Thanks.
And I would love to steam corrected. I'm very open to criticism, and if you can open my eyes to something else, I would be very happy. Yeah.
That's great. I guess we are closing the open discussion now at 6 sharp. So thank you so much, especially for the speakers, for the very nice talks. I think it conveyed a nice overview on what's the state of the art on AI for space, at least giving some insights related to the AI methodologies, the technologies we are building, the market in which we are operating, and some examples of recent startups working in this area. So thank you all again. We will close now the recording and the remote participation. We have a short, let's say, aperitif we can share with the persons in presence only, unfortunately. But then I will upload the entire recording on the official website. So if anyone else is interested or couldn't attend even this meeting, will be able to access it. And I will ask later on via email to the speakers to send me the slides if they want, so that we can upload them too. So thank you again, and I'll see you soon.
Thank you for organizing this and the opportunity.
Thank you.
Bye-bye.
Bye.
Bye-bye.
Bye.
Thank you. Bye.
Thank you. Cheers.